Hello there, and welcome to Science for Sleep. I'm glad you're here tonight. Wherever you happen to be listening from, whether it's late in the evening, very early in the morning, or perhaps sometime in the quiet middle of the night, you're in the right place to slow things down for a while and explore a question that is surprisingly big. Because tonight we're going to think about something that sounds simple at first, but becomes much more interesting the longer you sit with it. How long would it really take to cross our galaxy? Now, that question might not be something people usually think about while brushing their teeth or waiting in line at a grocery store. Most of us are busy dealing with things much closer to home: work, school, messages on our phones, deciding what to eat tomorrow. But every now and then, it's nice to zoom out a little. And when you zoom out far enough, you eventually arrive at the place where we are right now, inside a galaxy. Before we go any further, I'd like to ask you something small and personal. What time is it where you are? Maybe it's late, and the room around you is dim and quiet. Maybe there's a soft lamp on somewhere nearby, or the faint glow of a screen across the room. Or maybe you're listening with your eyes already closed, letting the sound of this story drift through your thoughts while you settle into sleep. And another question, just out of curiosity: where are you listening from tonight? You don't have to answer out loud, of course, but it's nice to imagine that people all over the world are listening to the same story at the same time. Different countries, different cities, different rooms, all connected by the same quiet curiosity about the universe. If you find this kind of slow exploration soothing, you can always support the channel by liking the video and subscribing. It helps more people discover these calm science journeys, and it lets me keep making them for you. Now, with all of that settled, let's begin. Imagine for a moment that you could step outside your home tonight and look up at the sky. Not just a quick glance, but really take a moment to look. If the sky above you is dark enough, you might see a faint hazy band stretching across it. It looks almost like a cloud, but thinner and more delicate. A pale river of light running from one horizon to the other. People have been seeing that glowing band for thousands of years, long before telescopes existed, long before anyone knew what stars actually were. Ancient cultures gave it many different names, but the one that stuck in English is the Milky Way. The name comes from the way it looks. A spilled streak of pale light across the darkness, almost like someone poured a thin stream of milk through the sky. For most of human history, nobody knew what that band really was. It looked like mist, or glowing dust. Some thought it was part of Earth's atmosphere. Others believed it was a pathway for gods or spirits. But then, about 400 years ago, a man named Galileo pointed a small telescope toward that glowing stripe, and something surprising happened. Instead of mist, he saw countless tiny stars, thousands of them, packed together so tightly that from far away they blend into a soft glow. What Galileo realized slowly and carefully was that the Milky Way isn't a cloud at all. It's a huge collection of stars. Today we know that collection is enormous beyond ordinary imagination. The Milky Way contains hundreds of billions of stars, possibly even more. Our sun is one of them. And Earth, the place where you're sitting or lying right now, is quietly travelling through space alongside that star. Which means something slightly strange is already true. You're already inside the galaxy we're talking about crossing. Not outside it, not observing it from far away, inside it. That's a bit like trying to understand the size of a forest while standing in the middle of it. When you're surrounded by trees, it's hard to see the full shape of the forest. All you see are trunks and branches nearby. The larger structure is hidden. The same thing happens with our galaxy. From Earth, we see stars in every direction, some brighter, some dimmer, some close, some incredibly far away. But because we are inside the Milky Way, we can't easily step back and see the whole thing at once. Astronomers had to figure out its shape slowly, using careful measurements and patient observation. And the picture that eventually emerged is fascinating. The Milky Way is shaped a little bit like a giant flat disk. Not perfectly flat, of course, more like a very thick pancake made of stars. At the centre of that disk sits a dense region packed with stars, gas, dust, and a supermassive black hole. Surrounding that centre are long spiral arms that curve outward like the arms of a spinning pinwheel. Our Sun lives in one of those spiral arms, not near the centre, not the very edge either, roughly halfway out, which means that when we look toward the night sky, we are looking through the galaxy from the inside. In some directions we see the crowded regions toward the centre. In other directions we see the thinner outskirts where stars become more spread out. All of that structure stretches across a distance that is extremely difficult to grasp, so instead of jumping directly to numbers right away, let's approach this slowly. Think about a city. If you live in a city, you might be used to travelling across it by car or bus. Maybe it takes 20 minutes to reach another neighbourhood. Maybe 40 minutes if traffic is heavy. Even large cities are manageable in that sense. Now imagine a country instead of a city. Driving across an entire country takes longer, sometimes many hours, sometimes days. And if you zoom out again to the size of a continent, suddenly even airplanes start to feel slow. Crossing an ocean might take 8 or 10 hours in a jet travelling hundreds of kilometres per hour. These distances feel large in daily life, but space operates on an entirely different scale. The distance between Earth and the Moon is about 384,000 kilometres. A spacecraft travelling to the Moon usually takes around 3 days to arrive, 3 days just to reach the closest world to Earth. Now let's stretch that distance further. The distance from Earth to the Sun is about 150 million kilometres. Light itself takes a little over 8 minutes to cross that gap. 8 minutes moving at the fastest speed anything can travel in the universe. Even that enormous distance, however, is tiny compared with the scale of our galaxy, because the Milky Way is roughly 100,000 light-years across. A light-year is the distance light travels in 1 year. Light moves incredibly fast, about 300,000 kilometres every second. In 1 second, light could circle the Earth more than 7 times. In 1 minute, it travels about 18 million kilometres. In 1 hour, the number becomes almost hard to say out loud. And in a full year, light travels about 9.46 trillion kilometres. So when astronomers say the Milky Way is about 100,000 light-years wide, they mean that light itself would need 100,000 years to travel from one side to the other. And remember, that's light, the fastest thing the universe allows. Which means something interesting is already becoming clear. If we wanted to cross the galaxy using anything slower than light, the journey would take even longer, much longer. That's the central puzzle we're going to explore together. Because when people first hear numbers like 100,000 light-years, it's easy to simply nod and move on. The number is so large that the mind almost refuses to hold on to it. But if we slow down and examine it piece by piece, something remarkable happens. The galaxy begins to feel more real. You start to imagine what a journey through it might look like. You might picture leaving the solar system behind, passing distant stars, drifting through enormous clouds of gas, moving slowly through the spiral arms that curve across the galaxy. Each of those regions contains its own strange environments, clusters of young stars being born, old stars nearing the end of their lives, dark regions filled with cold molecular clouds, invisible halos of dark matter surrounding everything. Travelling through all of that would be a journey far beyond anything humans have attempted before. Right now, the farthest human-made object from Earth is the Voyager 1 spacecraft. Voyager 1 was launched in 1977. After visiting Jupiter and Saturn, it continued travelling outward, leaving the planets behind and heading toward interstellar space. Even after almost 50 years of travel, Voyager 1 has only moved a tiny fraction of a light-year away from Earth. In fact, if you compared the size of the galaxy to the width of an entire continent, Voyager 1 would barely have stepped off the curb, which means that crossing the Milky Way with current technology would be, well, not exactly quick. But that's getting a little ahead of the story. Because before we can answer how long such a journey might take, we need to understand something even more basic: how wide the galaxy really is. Not just the number written in textbooks, but what that number means in terms of distance, time, and movement. Once we begin to explore that scale more carefully, the idea of travelling across the Milky Way becomes much easier to picture, and along the way we'll look at several different ways to attempt the trip: walking speed, cars, airplanes, modern spacecraft, even the speed of light itself. Each of those methods tells a slightly different story about the size of our galaxy, and each one reveals something new about the universe we live in. Exactly how wide is the galaxy we call home? Let's begin by settling into the place we already occupy in the universe, because before anyone can think about crossing a galaxy, it helps to understand what it means to live inside one. Right now, at this very moment, the ground beneath you feels steady. Your room feels still. The walls around you are quiet and unmoving. If you are lying down or sitting comfortably, everything probably feels calm and stable, exactly the way a resting place should feel. Yet something slightly surprising is happening. Earth is moving. It is rotating on its axis at roughly 1,600 kilometers per hour near the equator. At the same time, it is travelling around the Sun at about 107,000 kilometers per hour, and the Sun itself is moving through the Milky Way at a speed of roughly 800,000 kilometers per hour. All of that motion is happening while you sit perfectly still. The reason you don't feel it is simple. Everything around you is moving together. The air, the planet, the oceans, the atmosphere, even the spacecraft humans have launched into orbit. It is all drifting through space as one quiet, enormous system. And that system lives inside something even larger. The galaxy we call the Milky Way. When people first hear the word galaxy, they often picture something distant and separate. A glowing spiral photographed by a telescope, floating somewhere far away in deep space. But the Milky Way is not distant in that sense. It surrounds us. Every star you can see with your eyes at night is part of the Milky Way galaxy. The glowing band stretching across the sky is simply the densest region of that enormous structure. In other words, when you look up at the stars, you're not looking outward toward the galaxy, you're looking through it. Imagine standing inside a vast forest at night. Trees stretch in every direction. Some are close enough to touch, while others fade into darkness farther away. If the forest were dense enough and large enough, the combined glow of distant trunks might even create a faint misty brightness between them. That is not too far from what the Milky Way is like. Except instead of trees, the forest is made of stars, hundreds of billions of them. Astronomers estimate that the Milky Way contains somewhere between 100 billion and 400 billion stars. The exact number is still uncertain, partly because counting them all is extremely difficult. Stars cluster together, dust clouds hide some regions from view, and our position inside the galaxy limits what we can observe directly. Even so, the numbers involved are enormous. If you tried to count one star every second without ever stopping, it would take more than 3,000 years just to reach 100 billion, and that is only the lower estimate. Now consider something else. Most stars probably have planets. Over the past few decades, astronomers have discovered thousands of exoplanets orbiting distant stars. With each new telescope and each new observation technique, the number keeps growing. Some stars host giant gas planets larger than Jupiter. Others have small rocky worlds that may look a bit like Earth. Some systems contain multiple planets orbiting in complex patterns, which means the Milky Way may contain hundreds of billions of planets as well. Entire worlds scattered across the galaxy, each one orbiting its own sun, each one drifting through the same vast cosmic ocean. That is why the Milky Way can be described, in a very calm and literal way, as an ocean of stars. The stars are not evenly distributed like grains of sand. Instead, they form patterns, clusters, and spiral arms that sweep outward from the galactic centre. If you could view the galaxy from far above, you would see a broad disk with curved arms spiraling outward. The structure resembles a spinning pinwheel. At the centre lies a dense region known as the Galactic Bulge. This area contains many older stars packed closely together, along with clouds of gas and dust. Hidden deep within that region is a supermassive black hole called Sagittarius A star. Despite the dramatic name, Sagittarius A star is not actively consuming nearby stars the way some black holes do in other galaxies. It is relatively quiet at the moment, sitting calmly at the heart of the Milky Way while the galaxy rotates around it. Farther out from the centre, the spiral arms begin to stretch across the disk. These arms are not solid structures. They are more like traffic patterns in space. Stars move in and out of them over time, but the arms themselves remain as regions where gas and dust are compressed together. That compression triggers the birth of new stars. As giant clouds of gas collapse under their own gravity, new suns ignite and begin shining across the galaxy. Some of those newborn stars will shine for billions of years. Others will burn much faster, living brief but brilliant lives before exploding as supernovae. The cycle of star birth and star death continues endlessly across the Milky Way, quietly shaping the galaxy over immense stretches of time, and somewhere along one of those spiral arms sits our solar system. We are located in a smaller structure called the Orion Arm, sometimes referred to as the Orion Spur. It lies between two larger spiral arms known as Sagittarius and Perseus. This location turns out to be rather comfortable. We're not too close to the galactic centre, where radiation and gravitational disturbances are stronger. We're not too far out in the sparse outer regions either. Instead, we sit in a relatively calm neighbourhood. Stars here are spaced far enough apart that close encounters between solar systems are extremely rare. To give you an idea of how empty space really is, consider this. If our sun were the size of a small orange placed on a table, the nearest star would be another orange located roughly 2,000 kilometers away. That distance is roughly the width of a small country. Everything between those two oranges would be almost completely empty. This surprising emptiness is one reason why travelling between stars is so difficult. The stars may look close together when we see them in the night sky, but that appearance is misleading. Most of them are separated by vast distances. Even the nearest star system beyond our own, Alpha Centauri, lies about 4.37 light-years away. Light itself takes more than 4 years to make that journey, and once again, that distance is tiny compared with the full width of the galaxy. To cross the Milky Way from one side to the other, a traveller would need to pass through tens of thousands of light-years of space. Along the way, they would encounter many different environments. Some regions are filled with glowing nebulae where new stars are forming. Others contain ancient clusters of stars that have been travelling together for billions of years. There are enormous clouds of cold gas drifting through interstellar space, sometimes spanning hundreds of light-years. There are regions where powerful stellar winds carve bubbles in the surrounding gas, and scattered across the galaxy are the remnants of long-dead stars, white dwarfs, neutron stars, black holes, all of them quietly orbiting the centre of the Milky Way along with everything else. If someone truly attempted to cross the galaxy, their journey would pass through an incredible variety of cosmic landscapes. But before we imagine that journey in detail, it helps to pause for a moment and appreciate something important. The galaxy is not standing still. Every star inside it is moving. Our Sun completes one full orbit around the centre of the Milky Way, roughly every 230 million years. During that time, it travels through different regions of the galaxy, slowly drifting through the spiral arms. When dinosaurs roamed Earth, the Sun was in a different part of the galaxy than it is today, and hundreds of millions of years from now, it will be somewhere else again. This means that even if you stayed perfectly still relative to the Sun, you would still be travelling through the Milky Way simply by orbiting the galactic centre. In fact, during the time it takes you to listen to this video, our entire solar system will move thousands of kilometres through space. That motion is gentle and steady. There are no sudden jolts or dramatic turns. The stars drift along their orbits with quiet patience, guided by the combined gravity of the galaxy. Which brings us back to the question we are slowly approaching. If the Milky Way is such a vast ocean of stars, how long would it take to cross it? Somewhere inside a quiet spiral arm of the Milky Way, there is a star that most galaxies would consider completely ordinary. It is not unusually large. It does not shine with extreme brightness compared to the giants of the cosmos. It is simply a steady, middle-aged star burning hydrogen in a calm and predictable way. That star is our Sun. And circling that star, at just the right distance for oceans, clouds, and life to exist, is a small rocky world called Earth. From our everyday perspective, Earth feels like the centre of everything. The ground beneath us is where our homes are built. It is where cities grow, where forests spread, where oceans move with slow tides and changing seasons. Everything familiar to human experience happens here. Yet the moment we zoom outward even slightly, that comfortable sense of central importance begins to shrink. Earth is not the centre of the solar system. It is one planet among several that orbit the Sun. Mercury circles closer in. Venus glows bright in the evening sky. Mars travels on a wider path beyond our orbit, and farther out still lie the giant planets, Jupiter, Saturn, Uranus and Neptune, each surrounded by their own systems of moons. Even the solar system itself is not especially large compared with the galaxy around it. To picture our true cosmic address, it helps to think about how addresses work on Earth. If someone asked where you live, you probably would not answer with the name of the entire planet. Instead, you would begin with something specific. Maybe you would say the name of your street, then the city, then the country. Each level of the address adds a larger layer of location. The same idea works in space. Our smallest address is Earth. Earth belongs to the solar system. The solar system belongs to the Milky Way galaxy. And the Milky Way belongs to an even larger structure of galaxies called the local group. But for tonight, we will focus on the level where our journey across the galaxy would begin. That place is the solar system. At the centre sits the Sun, containing more than 99% of the total mass of everything orbiting around it. The planets, moons, asteroids and comets together make up only a tiny fraction of the system. The Sun formed about 4.6 billion years ago from a collapsing cloud of gas and dust. As gravity pulled that cloud inward, the material began spinning faster and flattening into a disk. Most of the gas gathered in the centre to form the Sun, while smaller clumps in the disk slowly merged into planets. Over time, those planets settled into stable orbits. Some became rocky worlds like Earth and Mars. Others grew into massive gas giants like Jupiter. And around one of those rocky planets, something remarkable eventually appeared. Life. Life that could look up at the sky and wonder where it lived. The solar system stretches much farther than most diagrams in textbooks suggest. The planets occupy only the inner region of a much larger space filled with smaller objects. Beyond Neptune lies the Kuiper Belt, a region populated by icy bodies left over from the early formation of the solar system. Pluto lives here, along with many other dwarf planets. Farther still is the Oort cloud, a distant spherical halo of icy objects that may extend tens of thousands of astronomical units away from the Sun. An astronomical unit, by the way, is the average distance between Earth and the Sun, about 150 million kilometres. Even at those vast distances, however, the Sun's gravity still reaches outward, gently holding these distant objects in loose orbits. If you travelled to the outer edge of the Oort cloud, you would be about halfway to the nearest star, and that nearest star is not particularly close. Proxima Centauri, part of the Alpha Centauri system, lies about 4.24 light-years away. Light itself takes more than 4 years to travel that distance. Our fastest spacecraft would need tens of thousands of years. That separation between stars might seem surprising when we remember how crowded the night sky appears. On a clear evening, thousands of stars can be visible at once. It can almost feel as if they are packed tightly together, but appearances can be misleading. Stars in the Milky Way are separated by enormous stretches of empty space. If the Sun were reduced to the size of a small marble, Earth would be a tiny grain of sand orbiting about a metre away. Neptune would circle roughly 30 metres out, and the nearest star would be another marble located hundreds of kilometres away. Everything in between would be almost completely empty. This emptiness is why interstellar travel is so difficult. The stars may look like neighbours, but the distances between them are immense. Our Sun sits inside a region known as the Orion Arm, sometimes called the Orion Spur. This structure is a smaller branch connecting two larger spiral arms of the galaxy. Those larger arms are named Sagittarius and Perseus. Spiral arms are not rigid structures. They behave more like waves of increased density moving through the galaxy. As gas and dust enter these regions, they become compressed, triggering the birth of new stars. Young stars often shine brightly within these arms, lighting up the surrounding clouds of gas. Over millions of years, stars drift out of the arms and continue orbiting the centre of the galaxy along slightly different paths. Our Sun likely formed in one of these spiral arms billions of years ago. Since then, it has been quietly travelling around the galactic centre, along with countless other stars. The distance between the Sun and the centre of the Milky Way is about 26,000 light-years. That means light leaving the galactic centre today would not reach us for 26,000 years. The number might sound large, but within the context of the galaxy it places us somewhere in the middle regions, not too close to the crowded core and not too far out toward the sparse edge. This location is sometimes described as part of the galaxy's galactic habitable zone. Closer to the centre, stars are packed much more tightly together. Supernova explosions are more frequent, and intense radiation can disrupt planetary systems. Farther out, heavy elements become less common. These elements are important for forming rocky planets like Earth, so our position, about halfway between the centre and the edge, appears to be relatively comfortable for long-term planetary stability. As the solar system travels through this region, it follows a path around the galaxy that takes roughly 230 million years to complete one full orbit. That means the last time our planet was in its current position relative to the galaxy, dinosaurs had not yet appeared. The continents on Earth looked completely different. Life was dominated by early reptiles and amphibians. Since then, the solar system has continued its quiet journey around the Milky Way, carrying Earth along with it. If you could somehow watch this motion from far outside the galaxy, you would see the Sun tracing a slow circular path around the galactic centre. But the path is not perfectly smooth. Stars drift slightly above and below the galactic disk as they orbit. They also interact gravitationally with nearby stars and gas clouds. Over billions of years, these interactions slowly alter the Sun's orbit. Yet even with those changes, the solar system remains part of the same general region of the galaxy. One small neighbourhood within an enormous stellar city. To appreciate how small our neighbourhood truly is, imagine standing in the middle of a large metropolitan area at night. Lights stretch in every direction, streets branch outward, buildings form clusters and districts across the city. Now imagine selecting a single house somewhere within that city. That house represents our solar system. The city itself represents the Milky Way galaxy. From the perspective of someone standing in that house, the rest of the city might feel distant and mysterious. But from high above, the house would be almost impossible to spot among millions of others. That is the scale we are dealing with when we talk about crossing the galaxy. Our solar system is simply one address among hundreds of billions, and every one of those addresses contains its own stars, planets, and potential stories. If someone began a journey from our location toward the opposite side of the Milky Way, they would start by leaving this quiet neighbourhood of stars. They would pass through regions where the density of stars slowly changes. They would move closer to or farther from the spiral arms. They might encounter clusters of stars travelling together through space, or vast clouds of gas where new suns are forming. Eventually, depending on the direction of travel, They might approach the dense central regions where stars are packed thousands of times closer together than they are here, or they might move outward toward the thin outer edges of the galaxy, where stars become more sparse and the darkness between them grows wider. But all of that lies far ahead in the journey. For now, we're still standing at the starting point, examining our cosmic address and understanding exactly where we are. Numbers have a strange effect on the human mind. When they become too large, they begin to lose their meaning. 1,000 feels understandable. 1,000,000 already stretches the imagination. 1,000,000,000 becomes difficult to picture clearly. And when we reach numbers used in astronomy, our brains often quietly give up trying to visualize them at all. The size of the Milky Way is one of those numbers. You will often hear a simple statement repeated in documentaries and textbooks. The Milky Way is about 100,000 light-years across. The phrase sounds impressive, but unless we slow down and unpack it carefully, it can slip past us without truly sinking in. So instead of rushing past the number, let's take our time with it. The first step is understanding the unit astronomers use to measure such enormous distances. That unit is the light year. Despite how it sounds, a light year is not a measure of time, it is a measure of distance. Light travels extremely fast. In fact, it moves faster than anything else in the universe, at about 300,000 kilometers every second. To get a sense of that speed, imagine circling the Earth 7 times in a single second. That is roughly how quickly light moves. Now let that motion continue for a full minute, then an hour, then an entire year. After 12 months of constant travel at that incredible speed, light will have crossed about 9.46 trillion kilometers. That distance is 1 light year. So when astronomers say the Milky Way is roughly 100,000 light years wide, they are saying something very specific. If a beam of light started on one edge of the galaxy and travelled in a straight line to the opposite edge, it would need 100,000 years to complete the trip, and that is the fastest possible journey allowed by the laws of physics. Already the scale is beginning to sound impressive, but the story becomes even more interesting when we look at how astronomers discovered this size in the first place. For most of human history, nobody knew how large the Milky Way actually was. The night sky appeared as a dome filled with stars, but there was no clear way to measure how far away those stars were. Everything changed during the early 20th century. Astronomers began developing new techniques to measure stellar distances, using objects called variable stars. These stars change brightness in predictable patterns, which allow scientists to calculate how far away they are by comparing their true brightness with how bright they appear from Earth. One of the most important astronomers working on this problem was Harlow Shapley. By studying variable stars located in clusters surrounding the Milky Way, he began mapping out the structure of the galaxy. His measurements revealed something surprising. The solar system was not near the centre of the Milky Way. Instead, we were located far out toward one side. This discovery was an important step in understanding the true size of the galaxy. As more observations accumulated over the decades, astronomers gradually refined their estimates. Today, most measurements suggest that the Milky Way's stellar disk stretches somewhere between 100,000 and 120,000 light-years from one edge to the other. That number refers to the main region where most of the galaxy's stars are located. But the Milky Way does not end neatly at that boundary. Beyond the visible disk lies a much larger and more mysterious structure known as the galactic halo. The halo contains older stars, globular clusters, and a vast amount of dark matter. Dark matter cannot be seen directly, but its gravitational influence reveals that it surrounds the galaxy in an enormous sphere. Some estimates suggest that this halo may extend more than 1,000,000 light-years from the centre. If that is true, then the Milky Way's gravitational reach is even larger than the familiar disk of stars. For the purpose of our journey across the galaxy, however, the most relevant measurement is the width of the main disk. That is the region where most stars, including our Sun, are located. So when we imagine travelling from one side of the Milky Way to the other, we're picturing a journey of roughly 100,000 light years. But there is another dimension we should consider as well. Galaxy is not perfectly flat. The Milky Way has thickness. If you could look at the galaxy from the side, the disk would appear slightly puffed up in the middle and thinner toward the edges. The central bulge rises thousands of light years above and below the disk. In the region where our Sun is located, the thickness of the stellar disk is roughly 1,000 light years. That means the galaxy is much wider than it is tall. You can think of it somewhat like a giant pancake made of stars, though even that comparison struggles to capture the scale involved. Inside that disk, stars orbit the centre of the galaxy along curved paths. Our Sun completes one full orbit around the galactic centre, approximately every 230 million years. Astronomers sometimes call this a galactic year. Since the formation of the solar system about 4.6 billion years ago, the Sun has completed only around 20 such orbits. In other words, during the entire history of Earth, the solar system has circled the Milky Way only a few dozen times. That slow motion gives us another clue about the size of the galaxy. To remain gravitationally bound while moving at the Sun's orbital speed, the Milky Way must contain an enormous amount of mass. Much of that mass comes from stars, gas and dust, but a large portion appears to come from dark matter. Dark matter does not emit light, but it exerts gravity. Without it, the stars in the outer regions of galaxies would fly away instead of continuing their orbits. The presence of dark matter helps hold the Milky Way together as it slowly rotates. Now let's return to the distance itself. 100,000 light years. To make that number feel a little more tangible, we can compare it with distances closer to home. The distance between Earth and the Moon is about 384,000 kilometers. The distance between Earth and the Sun is about 150 million kilometers. The distance to the nearest star beyond our solar system is about 4 light years. So even reaching the closest neighbouring star requires travelling several light years through space. Crossing the Milky Way would require travelling tens of thousands of times farther than that. And remember, even light itself would need 100,000 years to complete the trip. If you began such a journey during the time when early humans were first painting on cave walls, the light from your departure point would still be travelling across the galaxy today. By the time it reached the other side, human civilization might look completely different, if it still existed at all. That realization gives us an interesting perspective on our place within the galaxy. When we look at distant stars across the Milky Way, we are not seeing them as they exist right now. We are seeing them as they were thousands, sometimes tens of thousands, of years ago. Light from those stars has been travelling across the galaxy the entire time. Some of the stars we observe may have changed dramatically since the light left them. A few may have already exploded as supernovae. Others may have formed new planets, or undergone subtle shifts in brightness. But until their newer light arrives here, we cannot know those changes yet. The Milky Way is large enough that the galaxy we observe is always a mixture of different moments in time. Different regions are showing us different slices of the past. All of this helps explain why crossing the galaxy is such a fascinating idea. The journey would not only involve enormous distances, it would also involve travelling through different eras of the galaxy's history, observing stars whose light left them thousands of years earlier. A traveller moving slowly enough might even witness changes in the structure of the galaxy over time. But before imagining the full journey, there is still another important step. Knowing the width of the galaxy is helpful, but distance alone does not tell us how long the trip would take. Time depends on speed, and speed can vary enormously depending on the method of travel. Walking speed, driving speed, aircraft speed, spacecraft speed, and eventually the ultimate cosmic speed limit, the speed of light. Each of these possibilities leads to a very different answer. Some of those answers are surprisingly large, others are almost impossible to grasp. But they all begin with the same simple measurement we have been discussing, a galaxy about 100,000 light years wide, which means that once we begin calculating travel times, the results are going to stretch far beyond the scale of ordinary human journeys. Standing at the edge of a very large map can be an interesting experience. When the map is small, the distance between two places might look manageable. A finger can move from one side to the other in a second or two. But the map is only a representation. The real journey across the actual landscape would take far longer. Thinking about crossing the Milky Way works in a similar way. On diagrams shown in books or documentaries, the galaxy often appears as a neat spiral shape viewed from above, a glowing disk with curved arms wrapping around a bright centre. When you see that image, it can feel as if the distance from one edge to the other is simply a long line drawn across the picture. Yet that simple line represents roughly 100,000 light-years of space. To begin imagining the journey properly, it helps to place ourselves at a starting point. Our solar system sits about 26,000 light-years from the centre of the galaxy. That position means we're neither near the crowded core nor close to the outer edge. Instead, we occupy a middle region of the galactic disk, drifting through one of its quieter spiral structures. If someone set out from here and aimed for the far side of the Milky Way, they would need to travel through tens of thousands of light-years of interstellar space. At first glance, the surroundings might look surprisingly empty. Space between stars is not filled with glowing lights the way it sometimes appears in science fiction movies. The average distance between neighbouring stars in our region of the galaxy is several light-years. Even if a spacecraft were travelling toward another star, that star would remain a tiny point of light for most of the journey. But emptiness does not mean complete darkness or stillness. Between the stars drifts a thin mixture of gas and dust called the interstellar medium. Most of this material is extremely sparse, far thinner than even the best vacuum humans can create in laboratories on Earth. Yet over enormous distances, these tiny traces of matter become important. Interstellar gas forms clouds that stretch across many light-years. Some are warm and diffuse, others are cold and dense enough to collapse under gravity, eventually giving birth to new stars. A traveller crossing the galaxy would pass through many of these regions. Sometimes the surrounding space would glow faintly with the light of nearby stars reflecting off gas and dust. At other times, the view would become darker as thick clouds blocked distant starlight. Moving deeper into the galaxy would gradually reveal changes in the stellar environment. Closer to the centre, stars become more numerous. The sky from the perspective of a planet in those regions might appear far brighter than the sky above Earth. Instead of a few thousand visible stars, there could be tens of thousands or even millions scattered across the night. Clusters of stars also appear throughout the Milky Way. Some clusters are loose groups of relatively young stars that form together from the same gas cloud. Others are ancient globular clusters containing hundreds of thousands of stars packed tightly into spherical shapes. Passing near one of these clusters would be an unforgettable sight. Instead of a single sun dominating the sky, dozens or hundreds of stars might appear bright enough to cast faint shadows. Of course, the journey would also encounter the larger structures that shape the galaxy itself. The spiral arms of the Milky Way are regions where gas, dust and stars become slightly more concentrated. They are not solid arms made of fixed stars. Rather, they behave more like waves moving through the galactic disk. As stars orbit the centre of the galaxy, they drift in and out of these arms over time. Inside the arms, star formation is more active. Bright blue stars, which burn hot and live relatively short lives, often illuminate the surrounding gas clouds. Their radiation causes nearby nebulae to glow in soft colours. These glowing nebulae are some of the most beautiful objects astronomers observe. But a traveller crossing the galaxy would not move from one dramatic sight to another in quick succession. The distances between these regions are enormous. Even travelling at incredible speeds, the scenery would change slowly. Weeks, months, or even years might pass before a noticeable shift in the surrounding starfield occurs. The galaxy is vast enough that motion through it feels gentle rather than dramatic. Another important feature of the Milky Way would gradually come into view if the traveller moved toward the centre. The central bulge of the galaxy. This region is thicker and more densely populated with stars than the outer disk. It surrounds the galactic centre in a roughly spherical shape that rises above and below the flat plane of the galaxy. Within that crowded region lies a supermassive black hole known as Sagittarius A*. Despite its enormous mass, Sagittarius A* is not especially dangerous to objects far away from it. At a distance of tens of thousands of light years, its gravitational pull simply contributes to the overall structure of the galaxy. However, the environment near the centre is much more energetic than the quiet neighbourhood around our Sun. Stars move faster, interactions between them occur more frequently, and radiation levels are higher. Crossing the galaxy through the central regions would reveal an entirely different stellar landscape compared with the calmer spiral arms. But there is something important to remember while imagining this journey. The galaxy itself is moving. Every star is orbiting the centre along its own path. The Sun travels around the Milky Way at roughly 800,000 kilometers per hour. Other stars move at similar speeds, sometimes faster, sometimes slower depending on their distance from the centre. Because of this motion, the positions of stars slowly change over time. A journey lasting thousands or millions of years would not pass through a static galaxy. The stars themselves would be drifting along their orbits during the entire trip. Some would gradually approach, others would slowly move away. The spiral arms themselves would continue their pattern of star formation and movement. In other words, crossing the Milky Way would not be like crossing a frozen map. It would be more like navigating through a slowly flowing ocean. Everything is in motion. Another challenge of such a journey is the sheer scale involved. Travelling 1 light year already requires light itself to move for an entire year. That means even if a spacecraft could reach 10% of the speed of light, it would still need 10 years to travel a single light year. At that speed, crossing the full width of the galaxy would require about 1 million years. That number alone begins to reveal how ambitious the journey would be. But before calculating exact travel times, it is helpful to think about how humans usually experience travel. When we drive across a city, the trip might take 20 minutes. Crossing a country by airplane may require several hours. Flying across an ocean might take half a day. Each increase in distance requires a faster method of travel. So what happens when we apply that same logic to the galaxy? What if someone attempted to cross the Milky Way at ordinary human speeds? Consider the most ordinary kind of movement humans know: walking. It is slow, steady, and familiar. For thousands of years, walking was the main way people travelled across landscapes. Long before engines existed, people crossed valleys, climbed mountains, and followed winding roads using nothing more than their own footsteps. Even today, walking remains the most natural speed for the human body. A relaxed walking pace is usually around 5 kilometers per hour. Some people walk a little faster, some a little slower, but 5 kilometers per hour is a comfortable average. That speed feels perfectly reasonable when you're crossing a park, moving through a city street, or taking a quiet evening stroll. But when we apply that same speed to cosmic distances, something remarkable happens. The numbers begin to stretch far beyond anything we experience in daily life. To understand what walking across the galaxy would mean, we need to begin with the distance we discussed earlier. The Milky Way is roughly 100,000 light-years wide. A single light year is about 9.46 trillion kilometers. That means the full width of the galaxy is approximately 946 quadrillion kilometers. It is such a large number that it is almost impossible to visualize directly, so instead we will approach it step by step. Imagine that someone started walking across the galaxy at a steady pace of 5 kilometers per hour. They would walk continuously without stopping, no rest breaks, no sleep, just a constant motion forward through space. In 1 hour they would cover 5 kilometers. In 1 day they would travel about 120 kilometers. In 1 year of uninterrupted walking, they would move about 43,800 kilometers. Now pause for a moment and consider that number. 43,000 kilometers is roughly the circumference of Earth. If you walked continuously for an entire year at that steady pace, you would circle the entire planet once. That sounds impressive on a human scale. But compared with the distances between stars, it is almost nothing. The nearest star beyond our solar system, Proxima Centauri, lies about 4.24 light-years away. That distance equals roughly 40 trillion kilometers. At walking speed, covering that distance would take an extraordinary amount of time. To travel 40 trillion kilometers at 5 kilometers per hour, a person would need about 9 trillion hours of walking. Converting that into years produces a number that is difficult to grasp. It would take more than 1 billion years just to reach the nearest star, and that is only the closest neighbour. Crossing the entire Milky Way would require walking 100,000 light-years instead of 4. If we continue the calculation, the total journey would take about 25 trillion years. That is 25,000 billion years. To put that number in perspective, the universe itself is about 13.8 billion years old. Walking across the galaxy would take nearly 2,000 times longer than the entire age of the universe. In fact, if someone had started walking across the Milky Way at the moment the first stars formed in the universe, they would still be nowhere near the halfway point today. Of course, walking across space is not physically possible in the ordinary sense. There is no solid ground between stars, and the vacuum of space would make such a journey impossible without extraordinary life support systems. But the calculation still serves an important purpose. It helps us feel the scale of the galaxy in terms of something familiar. Walking is slow compared with cars, airplanes, or spacecraft. Yet even that humble speed allows us to explore entire continents over the course of months or years. The galaxy, however, is so vast that walking becomes almost meaningless as a method of crossing it. During those trillions of years, the universe itself would change dramatically. Stars do not live forever. Many of the stars currently shining in the Milky Way would exhaust their nuclear fuel long before the journey finished. Massive stars burn through their fuel quickly, sometimes lasting only a few million years before exploding as supernovae. Even smaller stars like our Sun have finite lifetimes. The Sun is about 4.6 billion years old today, and will likely continue shining for another 5 billion years before evolving into a red giant. Compared with a 25 trillion year journey, the lifetime of the Sun is incredibly short. That means the star that currently warms our planet would disappear long before the traveller reached the far side of the galaxy, and the galaxy itself would not remain unchanged during that time. The Milky Way is slowly drifting through space along with other nearby galaxies. Over billions of years, gravitational interactions between galaxies gradually reshape their structures. One of the most significant events expected in the distant future is the collision between the Milky Way and the Andromeda Galaxy. Astronomers estimate that this encounter will occur in about 4 billion years. When the two galaxies merge, their stars will pass through one another in a vast gravitational dance. Because the distances between stars are so large, direct collisions between stars will remain extremely rare. But the overall shape of the galaxy will change dramatically. The spiral structure of the Milky Way will likely dissolve, forming a larger elliptical galaxy sometimes nicknamed Milkomeda. If someone were walking across the galaxy for trillions of years, they would eventually witness this transformation firsthand. The galaxy they began walking across would gradually evolve into something entirely different. Even the stars themselves would change. After trillions of years, many of the brightest stars in the universe will have long since burned out. The cosmos will become dominated by smaller, dimmer stars that burn their fuel very slowly. The sky would look very different compared with what we see today. Some regions of the galaxy might grow darker as older stars fade away. Others might brighten temporarily when new stars form from collapsing clouds of gas. The traveller would experience a constantly changing universe, even though their own progress across the galaxy remained painfully slow. There is another interesting twist to consider as well. The Milky Way is rotating. Our Sun completes one orbit around the centre of the galaxy roughly every 230 million years. During a 25 trillion year journey, the galaxy would rotate more than 100,000 times. Stars that were once distant might pass closer to the traveller's path, while others drift farther away. In other words, the destination itself would not remain fixed. The galaxy would continue evolving and moving while the traveller took their slow steps across its enormous disk. All of this highlights a simple truth about cosmic distances. Human-scale speeds are completely overwhelmed by the size of the universe. Walking works beautifully for exploring a forest trail or a quiet city street. But when we expand our perspective to the scale of galaxies, even the longest human journeys shrink into something incredibly small. Fortunately, humans rarely rely on walking alone when travelling long distances. What if we tried to cross the galaxy not on foot but using vehicles much faster than walking? Human travel did not remain limited to walking for very long. Once wheels were invented, distances that once required days of walking could suddenly be crossed much more quickly. Later, engines arrived, turning carts into cars and ships into machines that could move far faster than wind or muscle alone. Eventually, airplanes lifted people above the ground entirely, shrinking continents and oceans into manageable trips measured in hours instead of months. Because of those inventions, modern travel feels fast. A car moving along a highway might cruise comfortably at around 100 kilometers per hour. A passenger airplane travelling high above the clouds can reach speeds close to 900 kilometers per hour. Rockets designed to escape the pull of Earth's gravity can accelerate even faster. When you experience those speeds firsthand, they feel impressive. Watching the landscape blur past the window of a car or looking down from an airplane as entire cities pass beneath you can give the sense that you are covering enormous distances very quickly. But the galaxy has a way of humbling even our fastest machines. To understand how these familiar speeds compare with cosmic distances, we can take the same journey we imagined before and simply increase the speed of travel step by step. The distance remains the same, roughly 100,000 light-years from one side of the Milky Way to the other. As mentioned earlier, 1 light-year equals about 9.46 trillion kilometers. That means crossing the galaxy involves travelling approximately 946 quadrillion kilometers. The number is enormous, but once we fix the distance, calculating travel time becomes straightforward. We simply divide that distance by the speed of the vehicle. Let us begin with a car. A typical highway speed for a car might be around 100 kilometers per hour. At that pace, the car travels about 2,400 kilometers in a single day. In 1 year of continuous driving without stopping, the distance would be around 876,000 kilometers. That is more than enough to circle Earth many times. In everyday terms, it feels like an extraordinary amount of travel. However, compared with the distances between stars, it is still very small. If someone drove a car across the entire width of the Milky Way at 100 kilometers per hour, the journey would take more than 1 trillion years. That is 1,000 billion years. To compare that with something familiar, remember that the universe itself is about 13.8 billion years old. A car travelling steadily across the galaxy would need roughly 70 times the age of the universe to finish the trip. Of course, driving a car through space would present many obvious problems. Cars rely on roads, gravity, and air. None of those things exist in interstellar space. But once again, the purpose of the calculation is not to design an actual vehicle for the journey. It is simply to reveal how the scale of the galaxy compares with the speeds humans are accustomed to. So if a car is far too slow, perhaps flying would help. Commercial airplanes typically travel at speeds around 900 kilometers per hour. At that pace, crossing an entire continent can take only a few hours. Flying across the Atlantic Ocean may take 7 or 8 hours depending on the route. From the perspective of someone living a few centuries ago, such speeds would seem almost magical. Yet even an airplane becomes slow when placed next to the Milky Way. At 900 kilometers per hour, an airplane travelling continuously would cover about 7.9 million kilometers in a year. That is roughly 50 times faster than our hypothetical car. But when we apply that speed to the galaxy's width, the journey still becomes astonishingly long. flying across the Milky Way at airplane speed would take roughly 120 billion years. That is more than 8 times the current age of the universe. Even at this much higher speed, the galaxy still refuses to become manageable, so we increase the speed again. Instead of a car or airplane, imagine a rocket. Rockets are designed to operate in space, and their speeds are far greater than anything that moves along roads or through the atmosphere. When spacecraft leave Earth, they must reach a velocity of about 11 kilometers per second to escape the planet's gravity. That speed is called escape velocity. 11 kilometers per second may not sound dramatic at first, but when converted into kilometers per hour, it becomes nearly 40,000 kilometers per hour. That is more than 40 times faster than a commercial jet. Some spacecraft travel even faster once they begin exploring the solar system. The Parker Solar Probe, which studies the Sun, reaches speeds exceeding 600,000 kilometers per hour when it swings close to the Sun during its orbit. For our thought experiment, let us consider a rocket travelling at a steady speed of 40,000 kilometers per hour, a reasonable figure for a spacecraft leaving Earth and continuing outward. At that pace, the rocket would travel about 350 million kilometers in a year. Now the numbers are beginning to look much more impressive, but the galaxy is still larger. If a rocket moved across the Milky Way at 40,000 kilometers per hour, the journey would take roughly 27 million years. That number is dramatically smaller than the trillions of years required for walking or driving. Yet it is still far beyond the length of human history. 27 million years ago, the world looked very different. Dinosaurs had already disappeared, but the Earth was still dominated by ancient mammals and early forms of life very different from those we know today. Humans did not exist. If a spacecraft had begun its journey across the galaxy at rocket speed during that distant era, it would still be travelling today and would not reach the far side for millions of years more. That perspective helps us understand why interstellar travel is such a difficult challenge. Even when using machines that move tens of thousands of kilometers per hour, the distances between stars remain enormous. And remember, crossing the entire galaxy involves passing not just one star system, but tens of thousands of them. Another interesting detail appears when we consider the motion of the galaxy itself. Our Sun orbits the centre of the Milky Way at roughly 800,000 kilometers per hour. That means the solar system is already moving faster than the rocket speed we just imagined. Yet despite travelling that quickly, the Sun still needs about 230 million years to complete a single orbit around the galaxy. In other words, even the natural motion of stars inside the Milky Way demonstrates how vast it truly is. Cars, airplanes and rockets represent huge achievements of human engineering. They allow us to explore our planet and even send machines to other worlds, but the scale of the galaxy stretches far beyond the capabilities of these technologies. To reduce the travel time significantly, we would need speeds far greater than anything humans have yet built. And that leads us to the next question. What happens when we look at the fastest spacecraft humanity has ever launched? Machines built for space travel behave very differently from the vehicles we use on Earth. Cars depend on roads and friction with the ground. Airplanes rely on air flowing over their wings. Rockets, however, operate in a place where there is no road and no air at all. They push themselves forward by throwing mass in the opposite direction. Hot gas blasts out of the engine, and the spacecraft moves forward in response. The process follows one of the simplest principles in physics. Every action has an equal and opposite reaction. Using that method, rockets can reach speeds that seem extraordinary compared with anything moving across the surface of our planet. A commercial jet cruising at 900 kilometers per hour already feels fast when you're sitting inside it. But spacecraft move far beyond that. When a rocket launches from Earth, it must first fight against the pull of gravity. Reaching orbit around Earth requires a speed of roughly 28,000 kilometers per hour. That number alone is more than 30 times faster than a passenger airplane, and escaping Earth entirely requires even more energy. Once a spacecraft leaves the gravitational grip of our planet and begins travelling through the solar system, its speed can continue increasing through clever navigation techniques. Engineers sometimes send spacecraft past planets in carefully planned flybys, using the planet's gravity to accelerate the probe even further. This method is called a gravitational assist. With enough planning, a spacecraft can gain enormous velocity by borrowing a tiny bit of momentum from a planet. Some of the fastest machines humans have ever built reach their incredible speeds this way. One of the most famous examples is the Voyager 1 spacecraft. Voyager 1 launched in 1977 during an ambitious mission to explore the outer planets. It passed by Jupiter and Saturn, sending back detailed images and measurements that transformed our understanding of those distant worlds. After completing its planetary tour, Voyager 1 continued travelling outward. Instead of stopping somewhere in the solar system, the spacecraft kept going. Today, it is more than 24 billion kilometers away from Earth and moving at roughly 61,000 kilometers per hour relative to the Sun. Even at that remarkable speed, however, Voyager 1 is still extremely close to home when compared with the scale of the galaxy. In fact, Voyager 1 has not even travelled a single light day yet. A light day is the distance light travels in one day. That distance is about 26 billion kilometers. So after nearly 50 years of travel, Voyager 1 has only just begun approaching the distance light could cross in 24 hours. Now remember that a light year contains 365 light days, and crossing the galaxy requires travelling about 100,000 light years. The difference between those numbers reveals just how enormous the Milky Way truly is. But Voyager 1 is not the fastest spacecraft humans have launched. Another probe, called the Parker Solar Probe, currently holds that record. The Parker Solar Probe was launched in 2018 with the goal of studying the Sun more closely than any spacecraft before it. Instead of staying far away, the probe dives repeatedly toward the Sun, passing through its outer atmosphere. During those close approaches, the spacecraft experiences enormous gravitational acceleration. At its highest speed, Parker Solar Probe travels more than 600,000 kilometers per hour. That is roughly 200 times faster than a commercial jet. It is also fast enough to circle the Earth in less than 4 minutes. If you were riding along on that spacecraft, continents would slide beneath you in moments. The entire planet would appear to spin rapidly below, but even this astonishing speed is still small compared with the distances between stars. To understand why, we can imagine a spacecraft travelling across the Milky Way at the speed of the Parker Solar Probe. 600,000 kilometers per hour sounds extremely fast, and on the scale of the solar system it truly is. But the galaxy stretches across about 946 quadrillion kilometers. When we divide that enormous distance by the probe's speed, we find that crossing the galaxy at 600,000 kilometers per hour would take roughly 180 million years. That number may seem surprising. After all, 600,000 kilometers per hour feels like an incredible velocity, yet the galaxy is so vast that even this speed produces a travel time longer than the entire age of the dinosaurs. 180 million years ago, Earth was a very different place. Dinosaurs dominated the land. The continents were arranged differently. Mammals existed only as small creatures living in the shadows of larger reptiles. If a spacecraft had left our solar system during that distant time and travelled continuously at Parker Solar Probe speed, it would still be in the middle of its journey today. The far side of the galaxy would remain tens of millions of years away. These comparisons help explain why interstellar travel is one of the greatest engineering challenges humans have ever considered. Spacecraft designed for exploring our own solar system move quickly enough to reach nearby planets within months or years. But the distances between stars are thousands of times larger. Even our fastest probes barely begin to scratch those distances. And there is another complication. Spacecraft launched from Earth do not maintain their maximum speed forever. Most missions rely on bursts of acceleration, followed by long periods of coasting. Over time, gravitational influences from the Sun and other objects gradually alter their trajectories. designing a spacecraft capable of maintaining extreme speeds across interstellar distances would require technologies far beyond what we currently use. Still, scientists have explored several ideas for reaching nearby stars more quickly. One proposal involves using powerful lasers to push extremely small spacecraft, equipped with reflective sails. The laser light would exert pressure on the sail, accelerating the probe to a significant fraction of the speed of light. Another concept involves nuclear propulsion systems capable of producing continuous thrust for long periods. These ideas remain largely theoretical for now, but they show how engineers are already thinking about the challenges of travelling beyond our solar system. Because ultimately, reaching other stars requires speeds much closer to the ultimate cosmic limit. That limit is the speed of light. Nothing with mass can travel faster than light according to our current understanding of physics. Light moves at about 300,000 kilometers per second, which is more than 1 billion kilometers per hour. Compared with the speed of light, even the Parker Solar Probe is moving slowly. The probe's record speed of about 600,000 kilometers per hour equals roughly 0.00056% of the speed of light. In other words, light travels nearly 2,000 times faster. That difference becomes very important when we consider journeys across the galaxy, because if travelling at hundreds of thousands of kilometers per hour still requires millions of years to cross the Milky Way, what would happen if we could travel at light speed itself? Light already crosses enormous cosmic distances every day. The light from distant stars travels across the galaxy before eventually reaching Earth. So imagining a journey at light speed provides an interesting way to understand the full scale of the Milky Way. And the answer reveals something both simple and astonishing. Even moving at the fastest speed the universe allows, crossing our galaxy would still take about 100,000 years. That realization changes the way we think about space, because it means the galaxy is not just big, it is vast on a scale that stretches far beyond the time span of civilizations. Light leaves a star and begins a journey that can last longer than civilizations. The moment a photon escapes the surface of a distant sun, it travels outward in a straight line at the fastest speed the universe allows. It does not slow down, and it does not grow tired. Once it begins moving, it continues across space at roughly 300,000 kilometers every second. That number is worth pausing on for a moment. 300,000 kilometers every second means light could circle the Earth more than 7 times in the span of a single heartbeat. In just 1 second, it could travel from New York to Los Angeles and back dozens of times. At that speed, the Moon is only about 1.25 seconds away from Earth. Light from the Sun takes about 8 minutes to reach our planet. Those 8 minutes are the time it takes sunlight to cross 150 million kilometers of empty space. Yet even that enormous distance is tiny compared with the size of our galaxy. So imagine something unusual for a moment. Instead of walking, driving, flying, or riding aboard a rocket, imagine travelling alongside a beam of light itself. Picture yourself moving through space at the same speed as the photons leaving a distant star. At that velocity, the solar system would vanish behind you almost instantly. The distance between Earth and the Moon would pass in a little more than a second. The orbit of Mars would slip by in minutes. The outer planets, Jupiter, Saturn, Uranus, Neptune, would fall behind in a matter of hours. Within a day, the entire solar system would feel surprisingly small. The orbit of Pluto would lie far behind, and the distant icy objects drifting in the Kuiper Belt would already be fading into the background. After several days of travel at light speed, you would reach the outer edges of the solar system, where the sun's influence begins to weaken. Farther out lies the Oort cloud, a vast spherical region filled with icy remnants from the early formation of the solar system. These objects orbit the sun at incredible distances, sometimes tens of thousands of astronomical units away. Even travelling at the speed of light, it would take roughly a year to cross the entire Oort cloud. And that moment marks something important. Leaving the Oort cloud means leaving the solar system behind. From there, the journey becomes truly interstellar. The nearest star system beyond our own is Alpha Centauri, located about 4.37 light-years away. Light leaving the Sun today will need more than 4 years to reach that neighbouring star. If you were travelling alongside that beam of light, the trip would take exactly the same amount of time, 4 years. 4 years to cross the distance between two neighbouring stars in the quiet suburbs of the Milky Way. Along the way, the view would remain surprisingly sparse. Stars would appear as distant points of light scattered across an enormous black background. Even as you move through space at incredible speed, the surrounding star field would change slowly. That is because the distances between stars are enormous. From our position in the Orion arm of the galaxy, most nearby stars are separated by several light-years. Even travelling at the fastest speed allowed by physics, reaching the next star still requires years of travel. But the journey across the galaxy involves far more than just one star system. Once you pass Alpha Centauri, the next stars appear ahead. Some are slightly closer, some much farther away. Each requires years of travel at light speed. Over time, the distances begin to accumulate. 10 light-years, 50 light-years, 100 light-years. Each milestone represents decades of travel even at the speed of light. After several centuries of moving through the galaxy, the surrounding pattern of stars would begin to shift more noticeably. Constellations would slowly rearrange themselves as the traveller moves deeper into new regions of the Milky Way. Clouds of gas and dust might appear along the path. Some would glow faintly as nearby stars illuminate them. Others would remain dark, blocking light from stars behind them. Passing through these regions could reveal enormous nebulae stretching across dozens or even hundreds of light-years. These clouds are the birthplaces of new stars. Gravity slowly pulls gas together until the pressure becomes great enough to ignite nuclear fusion in the core of a newborn sun. A traveller moving at light speed would watch these star-forming regions slide past over the course of decades. Eventually the route might lead toward one of the galaxy's spiral arms. Spiral arms are not rigid structures filled with permanently fixed stars. Instead, they behave more like waves of higher density moving through the galactic disk. Gas clouds entering these regions become compressed, triggering bursts of star formation. Because of that process, spiral arms often glow with the light of young, hot stars. Crossing one of these arms at light speed might take thousands of years. During that time, the sky would grow more crowded with bright stars. Stellar clusters and glowing nebulae would appear more frequently. The surrounding environment would feel richer and more active than the quieter regions between the arms, but the journey would continue. Beyond the spiral arms lies the central bulge of the galaxy. This region surrounds the galactic center and contains a much higher density of stars. From the perspective of a traveller approaching it, the sky might appear dramatically brighter. Instead of isolated points of light scattered across darkness, the entire sky could glow with the combined light of countless nearby stars. Deep within that crowded region sits Sagittarius A star, the supermassive black hole at the heart of the Milky Way. Despite its enormous mass, the black hole would not necessarily appear dramatic from a great distance. Its presence would reveal itself mainly through the motion of nearby stars orbiting at incredible speeds. Passing through the central bulge would likely take several thousand years, even at light speed. Eventually, the traveller would emerge on the opposite side of the galaxy, and the journey would continue through another sequence of spiral arms, star clusters, and interstellar clouds. All of that travel adds up. The Milky Way is roughly 100,000 light-years wide. That means even a beam of light needs 100,000 years to cross from one side to the other. If someone began riding alongside a photon today, they would reach the far edge of the galaxy long after the civilizations of Earth had changed beyond recognition. 100,000 years ago, early humans were still living in small groups scattered across the planet. Agriculture had not yet been invented. Cities did not exist. During the next 100,000 years, human culture transformed the planet dramatically. Now imagine that entire span of time as the length of a journey across the Milky Way at the speed of light. That comparison gives us a powerful sense of the galaxy's scale. Even the fastest possible traveller would spend longer crossing the galaxy than recorded human history. But there is an important detail we should consider before continuing. Travelling at the speed of light is not actually possible for objects that have mass. Photons can move at that speed because they have no mass. Particles like protons, atoms, spacecraft, or human beings behave differently. As an object with mass accelerates closer to the speed of light, the energy required to increase its speed grows dramatically. Eventually, the required energy becomes effectively infinite. That means no matter how powerful a rocket engine might be, it cannot accelerate a massive object all the way to light speed. This limit is one of the key insights from Einstein's theory of relativity. Understanding that limit changes how we think about interstellar travel. Because if even light itself needs 100,000 years to cross the galaxy, and objects with mass cannot quite reach that speed, then any realistic journey across the Milky Way would take even longer. Which raises a natural question. Why exactly does physics prevent massive objects from reaching the speed of light? And what happens as something moves closer and closer to that ultimate cosmic limit? Speed seems simple at first. Something moves, and we measure how fast it travels across a certain distance. A bicycle rolls along a road, a car drives across a highway, an airplane crosses an ocean. In everyday life, it often feels as though speed could keep increasing forever if we simply built better engines. Yet the universe has a rule that quietly stops this idea. There is a speed limit built into the fabric of reality itself. That limit is the speed of light. Light travels through empty space at about 300,000 kilometers per second. Nothing in the universe has ever been observed moving faster than this. Not particles, not signals, not spacecraft, not anything with mass. For a long time, scientists did not fully understand why this limit exists. In fact, before the 20th century, many people assumed that speeds could increase indefinitely. If you applied enough force, an object could always move faster. But then a new understanding of space and time began to emerge. The key figure behind this shift was Albert Einstein. In 1905, Einstein introduced a theory that would completely change the way physicists think about motion. This theory is now known as special relativity. Instead of treating space and time as separate, unchanging backgrounds, special relativity revealed that they are deeply connected. Space and time combine into a single structure called space-time, and the way objects move through space-time follows rules that are very different from everyday intuition. One of the most surprising consequences of this theory is that the speed of light is constant. No matter how fast you are moving, light always travels at the same speed relative to you. If you were standing still and shining a flashlight, the beam would move away from you at the speed of light. If you were travelling inside a spacecraft at half the speed of light and turned on the same flashlight, the beam would still move away from you at the speed of light. The universe does not allow the speeds to simply add together in the way we might expect. To make sense of this strange behaviour, space and time themselves adjust. Time can slow down. Lengths can contract. These effects are extremely small at everyday speeds, which is why we do not notice them in daily life. But as objects move faster and faster, approaching the speed of light, these changes become more dramatic. One way physicists describe this behaviour is through the relationship between energy and motion. As an object accelerates, it gains kinetic energy. In classical physics, that energy simply increases as the object moves faster. But special relativity introduces an additional factor. The closer an object's speed gets to the speed of light, the more difficult it becomes to accelerate further. Each small increase in speed requires a larger amount of energy than the last. Eventually, the required energy becomes enormous. In fact, the equation describing relativistic energy reveals something remarkable. E equals mc squared. This famous expression connects mass and energy. It tells us that mass itself is a form of energy, and that even a small amount of mass contains an enormous quantity of energy when multiplied by the square of the speed of light. When an object moves faster, part of the energy used to accelerate it effectively increases its relativistic mass. The faster it goes, the harder it becomes to push it faster still. As the object's speed approaches the speed of light, the energy required to accelerate it further grows without limit. Reaching the speed of light would require infinite energy, and since infinite energy is impossible to produce, the object can never quite reach that speed. This rule applies to anything with mass. Atoms, spacecraft, planets, and human beings all have mass. Because of that, they can accelerate toward the speed of light, but they can never fully reach it. Photons, the particles that make up light itself, behave differently. Photons have no rest mass. Because of that, they do not need to accelerate up to the speed of light. They simply exist moving at that speed from the moment they are created. In other words, light does not gradually speed up. It begins its journey already travelling at the universal speed limit. That difference explains why light can cross enormous distances so efficiently, while massive objects struggle to approach the same velocity. Another surprising consequence of special relativity appears when we consider the experience of time. As an object moves faster, time for that object begins to pass more slowly, relative to observers who remain at rest. This phenomenon is known as time dilation. The mathematical expression describing it looks like this. T prime equals t over the square root of 1 minus v squared over c squared. Here, t represents time measured by an observer who is not moving relative to the event, while t prime represents time experienced by someone moving at velocity v. The symbol, c, represents the speed of light. As the velocity, v, approaches the speed of light, the denominator becomes smaller and smaller. That means the time experienced by the moving traveller slows dramatically. At speeds close to light speed, time dilation becomes extremely significant. From the perspective of someone inside a fast-moving spacecraft, a long journey might feel surprisingly short. However, observers watching from Earth would measure a much longer passage of time. These effects have already been measured in experiments. Atomic clocks placed on fast-moving aircraft run slightly slower than identical clocks left on the ground. Particles accelerated in laboratories survive longer than expected because their internal clocks are slowed by their motion. Relativity is not just a theoretical curiosity, it has real, measurable consequences. The navigation systems used by GPS satellites must account for relativistic effects in order to remain accurate. Without those corrections, location errors would grow by kilometers within a single day. Returning to the idea of crossing the galaxy, these rules have important implications. Even if humanity developed a spacecraft capable of reaching speeds extremely close to the speed of light, the journey across the Milky Way would still require enormous amounts of energy. The closer the spacecraft moved to light speed, the more energy would be required for each additional increase in velocity. Eventually, the cost would become impractical. That is why most realistic proposals for interstellar travel aim for speeds that are only a small fraction of the speed of light. Even those fractions would represent incredible technological achievements. A spacecraft travelling at 10% of the speed of light would still require about 1 million years to cross the Milky Way. At 50% of the speed of light, the trip would take roughly 200,000 years from the perspective of observers on Earth. Even with time dilation affecting the travellers aboard the ship, the distances involved remain enormous. The universe, it seems, has built its scale carefully around this fundamental speed limit. Galaxies stretch across tens of thousands of light years. The spaces between them span millions of light years. The observable universe itself extends across tens of billions of light years. All of these distances are measured using light itself as the standard. Light is the cosmic messenger. It carries information from distant stars, galaxies and nebulae across the vastness of space. By the time that light reaches our telescopes, it often carries stories from the distant past. Some of the light we observe tonight left its source thousands or even millions of years ago. In a very real sense, astronomy is the study of ancient messages arriving across cosmic distances. Understanding why nothing with mass can reach light speed helps explain why those messages take so long to arrive. It also reveals why travelling across the galaxy is such a difficult challenge, because even the fastest possible traveller cannot simply leap across space instantly. The universe insists that journeys take time, and the Milky Way is large enough that even the fastest journeys stretch across thousands or hundreds of thousands of years. Nothing in the galaxy is truly standing still. Even though the night sky appears calm and unchanging from one evening to the next, every star in the Milky Way is quietly moving through space. The motion is slow on human timescales, which is why the constellations look the same year after year. But given enough time, the entire structure of the galaxy shifts and flows like a very gentle current. The Milky Way is not a rigid disk made of fixed stars. It behaves more like a vast rotating system, where billions of stars orbit a shared centre under the influence of gravity. Each star follows its own path, shaped by the combined pull of all the mass within the galaxy. To picture this, imagine a large carousel slowly turning in the dark. The horses on the carousel do not all move at exactly the same speed. Those near the outer edge must travel farther in order to complete a full circle, while those closer to the centre move along shorter paths. Something similar happens inside the Milky Way. Stars orbit the galactic centre at enormous speeds, yet the size of the galaxy is so great that the full journey around the centre takes an extraordinary amount of time. Our own sun is part of this motion. At this moment, the solar system is travelling around the centre of the Milky Way at roughly 800,000 kilometers per hour. That number may sound astonishing when compared with the speeds of cars or airplanes, but on the scale of the galaxy, it is simply the natural pace required to maintain orbit. Despite moving that quickly, the Sun still needs about 230 million years to complete a single orbit around the galactic centre. Astronomers sometimes call this span of time a galactic year. It is much longer than the year we experience on Earth, which is defined by our planet's orbit around the Sun. One Earth year lasts 365 days. One galactic year lasts about 230 million Earth years. To place that in perspective, consider the history of life on our planet. When the dinosaurs first appeared around 230 million years ago, the solar system was roughly in the same position within the galaxy that it occupies today. Since that time, Earth has completed only one full orbit around the Milky Way. During that single galactic year, the continents drifted across the planet's surface. Dinosaurs rose and vanished. Mammals spread across the land. Humans eventually appeared and built civilizations. All of that happened during one quiet loop around the galaxy. This slow rotation reveals an important detail about the Milky Way structure. If the galaxy were rotating like a solid object, the inner regions would move much faster than the outer regions. That would cause the spiral arms to wind up tightly over time, eventually twisting into a tangled shape. But observations show that the spiral arms remain visible for long periods. The reason lies in the way stars orbit the centre. Instead of rotating as a solid disk, the galaxy follows a pattern known as differential rotation. Stars closer to the centre complete their orbits more quickly than stars farther away. Yet the difference is not as extreme as simple gravity would predict. This unexpected behaviour led astronomers to one of the most intriguing discoveries in modern astrophysics. The galaxy appears to contain far more mass than we can see. When scientists measure the speeds of stars at different distances from the galactic centre, they find that the outer stars move faster than expected. According to the visible matter alone, those stars should drift away into intergalactic space, but they do not. Something unseen is holding them in place. This mysterious substance is known as dark matter. Dark matter does not emit light, and it does not interact with ordinary matter in ways we can easily detect. yet its gravitational influence shapes the motion of stars and galaxies throughout the universe. The Milky Way appears to be surrounded by a massive halo of dark matter extending far beyond the visible disk of stars. Without that halo, the galaxy would not rotate the way it does. Returning to the idea of travelling across the Milky Way, this slow rotation has interesting consequences. Imagine setting out from the solar system on a journey toward the far edge of the galaxy. Even if your spacecraft moved in a straight line, the stars around you would continue their own orbital motion. Over thousands or millions of years, the galaxy would slowly rearrange itself as different stars drifted along their paths. Constellations would gradually change shape. New stars would appear along your route, while others would move out of view. The galaxy would not remain frozen during your journey. Instead, it would behave more like a vast river of stars flowing through space. The spiral arms themselves are also part of this dynamic motion. Although they appear as bright curved structures when viewed from afar, spiral arms are not permanent groups of specific stars. They function more like waves travelling through the galactic disk. Gas clouds entering these waves become compressed, triggering bursts of star formation. Bright young stars illuminate the surrounding gas, making the arms visible across enormous distances. As stars age and drift away from the arms, new ones take their place. This continuous process keeps the spiral pattern visible even as individual stars move through it. For a traveller crossing the galaxy, these changes would unfold slowly but steadily. At first, the surrounding sky might look familiar. The patterns of stars would resemble the constellations seen from Earth, but over centuries and millennia, those patterns would gradually shift. Stars that once formed recognizable shapes would drift apart. New alignments would appear as the traveller moved through different regions of the galaxy. Eventually, the original constellations would vanish entirely. This transformation would occur not because the stars themselves disappeared, but because the observer had moved so far from the original viewpoint. Perspective plays an important role in astronomy. The constellations we see from Earth are simply patterns formed by stars located at very different distances. If you travelled even a few light years away, those patterns would begin to change. Crossing thousands of light years would transform the sky completely. Another effect of galactic rotation involves the journey itself. Because stars are orbiting the galactic centre, a traveller heading toward a particular destination would need to account for the motion of that destination over time. If the journey lasted millions of years, the star system being targeted might move significantly along its orbit before the traveller arrived. This challenge resembles trying to intercept a moving ship across an ocean rather than aiming for a stationary island. The galaxy is not static, and its constant motion adds complexity to any long-distance voyage. Even so, the overall structure of the Milky Way remains stable across long stretches of time. The combined gravity of billions of stars and vast clouds of gas keeps the galaxy bound together. While individual stars drift along their orbits, the general shape of the galaxy persists. The central bulge remains crowded with ancient stars, the spiral arms continue forming new suns, and the disk of the galaxy slowly turns as the stars circle their shared centre. From our position within the Orion Arm, the motion is subtle. The night sky changes so slowly that generations of observers see almost the same patterns of stars. But if someone could watch the galaxy from far outside, over millions of years, the motion would become clear. The Milky Way would appear as a slowly rotating spiral, its arms sweeping through space while the stars trace graceful orbits around the centre. And somewhere within that turning disk, our solar system continues its quiet journey. The Sun, Earth, and everything familiar to us are passengers in this long galactic orbit, which means that even if we never leave our home planet, we're still travelling through the Milky Way, slowly, steadily, completing one orbit every few 100 million years. Stars are often described as if they are fixed points in the sky. For most of human history, that description made sense. When people looked up at the night sky, the stars appeared to hold the same positions night after night, year after year. Constellations such as Orion, Ursa Major, or Cassiopeia seemed permanent, like patterns carefully drawn across the darkness. But the stillness of the sky is an illusion created by time. Human lives are short compared with the slow rhythms of the galaxy. The stars move constantly, yet their motion is so gradual that it takes centuries or even thousands of years before those changes become obvious. In reality, every star in the Milky Way is drifting through space. Some travel in gentle paths that circle the galaxy's centre, much like the Sun does. Others follow more complex orbits that carry them slightly above and below the flat disk of the galaxy. A few move on the unusually fast trajectories that send them racing through the Milky Way like cosmic travellers passing through an enormous ocean. Because of this constant motion, the galaxy behaves less like a rigid structure and more like a vast sea of stars. The stars do not remain anchored in one place. They flow through space, guided by gravity, each following a path shaped by the mass of the galaxy and the influence of nearby stars. Astronomers often refer to this motion as stellar drift or proper motion. Proper motion is the slow change in a star's position across the sky as seen from Earth. Measuring this motion requires extremely precise observations over long periods of time. The shifts are small, usually only fractions of a degree over an entire human lifetime. But modern instruments are sensitive enough to detect them. When astronomers track these tiny movements carefully, they discover that the stars are not standing still at all. They are gliding through the galaxy. Our own Sun is one of those wandering stars. As mentioned earlier, the Sun orbits the centre of the Milky Way once every 230 million years. During that orbit, it does not remain perfectly fixed within the galactic disk. Instead, the solar system gently bobs up and down through the disk as it travels. Right now, we happen to be passing through the middle region of the galaxy's disk. But over tens of millions of years, the Sun will gradually move slightly above the disk before drifting back downward again. This slow vertical motion is caused by gravitational interactions with the surrounding stars and gas clouds. The effect is subtle, but it means that our position within the galaxy is constantly changing. The Sun is not the only star with this wandering behaviour. Every star experiences gravitational nudges from its neighbours. When two stars pass relatively close to one another, their gravitational fields interact. Each star tugs slightly on the other, altering their paths just a little. These encounters are usually gentle because the distances between stars are enormous. Even in crowded regions of the galaxy, stars rarely come dangerously close. Yet over millions or billions of years, those tiny gravitational nudges accumulate. The result is that stellar orbits slowly evolve. Stars that once travelled on nearly circular paths around the galactic centre may gradually develop more elongated or tilted orbits. Some stars wander far from their original birthplaces. Others remain within loose groups known as stellar streams. Stellar streams are long trails of stars that move together through the galaxy. Many of these streams formed when smaller star clusters or dwarf galaxies were torn apart by the Milky Way's gravity. As those systems disintegrated, their stars spread out along their original orbital paths, creating extended rivers of stars flowing through the galactic halo. If a traveller were crossing the Milky Way, encountering one of these stellar streams could be a remarkable experience. Instead of isolated stars scattered across space, there might be a long chain of suns drifting together in a shared direction. Each star would still be separated by vast distances, but their collective motion would reveal that they once belonged to the same system. Another fascinating category of wandering stars are runaway stars. Runaway stars move through the galaxy at unusually high speeds compared with their neighbours. Some were accelerated by close encounters with other stars in dense clusters. Others were ejected when one member of a binary star system exploded as a supernova. When that explosion occurs, the gravitational balance of the system changes suddenly. The surviving star may be flung away at tremendous speed, racing through the galaxy on a new trajectory. A few runaway stars travel so quickly that they can escape the Milky Way entirely. These rare objects are called hypervelocity stars. Hypervelocity stars likely originate near the galaxy's central black hole. When two stars pass close to the black hole together, complex gravitational interactions can sling one of them outward at extraordinary speeds. The ejected star may leave the galaxy altogether, becoming an intergalactic wanderer drifting through the vast space between galaxies. Such events are rare, but they demonstrate how dynamic the galaxy truly is. The Milky Way is not a calm, perfectly ordered structure. It is a living system shaped by countless gravitational interactions unfolding over billions of years. For someone travelling across the galaxy, this constant motion would create a slowly shifting landscape. The stars surrounding the spacecraft would not remain fixed relative to one another. Some would drift closer, others would gradually move away. The background patterns of stars would evolve as the traveller moved through different regions of the galaxy. Constellations would dissolve and reform. New clusters of stars would appear along the route, while familiar patterns would fade into the distance. Over centuries or millennia of travel, the sky itself would transform. Even our nearest stellar neighbours are slowly changing their positions. Proxima Centauri, the closest known star to the Sun, is moving relative to our solar system. Over tens of thousands of years, the distance between our stars will change slightly as both systems continue their orbits around the galactic centre. In fact, the identity of the nearest star to the Sun will not remain the same forever. Different stars will pass closer to the solar system over millions of years before drifting away again. One future visitor is a star called Gliese 710. Astronomers have calculated that Gliese 710 will pass relatively close to the solar system in about 1.3 million years. Its approach will not threaten Earth, but it may disturb the distant objects in the Oort cloud, sending comets toward the inner solar system. Events like this are part of the natural wandering of stars through the galaxy. They remind us that the Milky Way is not frozen in place. Its stars are travellers, each following their own long journey through space. Some of these journeys are quiet and predictable, like the steady orbit of our Sun around the galactic centre. Others are more dramatic, shaped by gravitational encounters or stellar explosions. All of these motions contribute to the constantly evolving structure of the galaxy. For a spacecraft attempting to cross the Milky Way, these wandering stars would create a subtle sense of motion even in the surrounding sky. The traveller would not simply move through empty space between fixed stars. Instead, they would navigate through a slowly flowing sea of suns, each carrying its own planetary systems and histories. Looking up at the night sky gives the impression that the Milky Way is made entirely of stars. Thousands of bright points sparkle against the darkness, and the faint band of light stretching across the sky suggests a dense river of distant suns. For a long time, this was the only part of the galaxy humans could see. But the visible stars are only a small portion of the Milky Way's true structure. Much of the galaxy is hidden from our eyes. Vast amounts of material fill the spaces between stars, and even larger amounts of matter exist that we cannot see at all. These invisible components quietly shape the form of the galaxy and control how it moves. Understanding this hidden structure changes the way we imagine crossing the Milky Way. Because travelling across the galaxy would not simply mean passing from star to star. It would involve moving through a layered environment made of gas clouds, dust lanes, magnetic fields, and an enormous halo of unseen matter surrounding everything. One of the first invisible features astronomers discovered was interstellar gas. The space between stars is not completely empty. It contains a thin mixture of hydrogen, helium, and trace amounts of heavier elements. In most places, this gas is extremely diffuse, with only a few atoms occupying each cubic centimetre of space. Compared with Earth's atmosphere, which contains billions of particles in the same volume, interstellar gas is almost unimaginably sparse. Yet when spread across the vast distances of the galaxy, this thin material becomes significant. Enormous clouds of interstellar gas drift through the Milky Way. Some stretch across dozens or even hundreds of light years. These clouds are the raw material from which new stars are born. When gravity pulls regions of gas together, the density slowly increases. As the gas compresses, it begins to heat up. Eventually, the pressure in the center becomes high enough to ignite nuclear fusion, creating a newborn star. These stellar nurseries are some of the most important structures in the galaxy, even though they are often difficult to see. Many of them are hidden inside thick clouds of dust. Interstellar dust is another invisible ingredient shaping the Milky Way. These tiny particles are made of carbon, silicates, and other elements forged inside previous generations of stars. When stars explode as supernovae, they scatter these particles into space. Over time, dust accumulates within the galaxy, mixing with gas to form dense molecular clouds. Dust has a powerful effect on starlight. It absorbs and scatters visible light, blocking our view of objects behind it. When astronomers observe the Milky Way with ordinary telescopes, many regions appear dark not because they contain nothing, but because thick dust clouds hide the stars beyond them. One famous example is the Great Rift in the Milky Way, a series of dark lanes cutting across the bright band of the galaxy in the night sky. These lanes are not empty spaces. They are dense regions filled with dust that prevents distant starlight from reaching us. To see through these clouds, astronomers use telescopes sensitive to infrared and radio wavelengths. These forms of light can pass through dust more easily, revealing the hidden structures inside the galaxy. When viewed in infrared light, the Milky Way looks very different from the familiar band we see with our eyes. Dense clouds glow softly as warm dust radiates energy. Star-forming regions appear as bright clusters embedded within these clouds. The galaxy begins to resemble a complex web of gas and dust, rather than a simple collection of stars. But even this intricate network is not the full story. Beyond the gas and dust lies a much larger and stranger structure. Surrounding the entire Milky Way is a massive halo of dark matter. Dark matter does not emit or reflect light, so it cannot be observed directly with telescopes. Yet its gravitational influence is unmistakable. When astronomers measure how stars orbit the center of the galaxy, they find that the visible mass alone cannot explain the observed speeds. Stars far from the galactic center move much faster than expected. Without additional mass holding them in orbit, those stars should drift away into intergalactic space. Instead, they remain bound to the galaxy. The simplest explanation is that an enormous amount of unseen matter surrounds the Milky Way, creating a gravitational framework that keeps the galaxy intact. This invisible halo may extend hundreds of thousands of light years beyond the visible disk. In other words, the galaxy we see, the spiral arms, the central bulge, the clusters of stars, is only the bright inner portion of a much larger structure. If someone attempted to cross the Milky Way, they would be travelling through only the densest inner region of an even larger gravitational system. Another hidden feature shaping the galaxy is its magnetic field. Just as Earth has a magnetic field surrounding it, the Milky Way possesses a vast magnetic structure that stretches across the galactic disk. These magnetic fields influence the motion of charged particles drifting through interstellar space. Cosmic rays, which are high-energy particles accelerated by supernova explosions and other energetic events, spiral along these magnetic field lines as they move through the galaxy. Although we cannot see magnetic fields directly, astronomers detect them by observing how they affect the polarization of light and the motion of charged particles. Together, these invisible components, gas, dust, dark matter, and magnetic fields, form the hidden architecture of the Milky Way. They shape how stars form, how the galaxy rotates, and how matter flows through space over billions of years. For a traveller crossing the galaxy, these structures would influence the journey in subtle ways. Dense molecular clouds might appear as enormous dark regions blocking distant starlight, Star-forming nebulae could glow softly in surrounding radiation. Cosmic rays and magnetic fields would fill the space between stars, creating an environment far more dynamic than empty vacuum. Even the shape of the galaxy itself depends on these hidden elements. The spiral arms form where gas clouds become compressed by gravitational waves moving through the galactic disk. Dark matter provides the gravitational stability needed to hold the entire structure together. Without these invisible components, the Milky Way would look and behave very differently. Understanding this hidden structure also helps explain why the galaxy has such a distinctive shape. If you could travel far above the Milky Way and look down on it from outside, you would see a broad rotating disk with curved spiral arms stretching outward from the centre. The disk itself is about 100,000 light-years across, but only a few thousand light-years thick. Above and below that disk lies the galactic halo, extending much farther into space. Inside the disk, gas clouds collapse to form new stars. Supernova explosions scatter heavy elements and dust back into the interstellar medium. Over time, the material mixes and recycles through the galaxy. This slow cycle of birth, evolution and destruction continues across billions of years. Stars form, stars shine, stars eventually die, and the material from those stars becomes the building blocks for future generations. All of this activity takes place within the invisible framework holding the galaxy together, which means that crossing the Milky Way would involve passing through a complex environment shaped by forces that are often hidden from direct view. The journey would not simply be a long trip through empty space. It would be a passage through a layered cosmic ecosystem. Star-forming clouds, ancient stellar clusters, dark lanes of dust, invisible halos of dark matter, and the faint glow of distant suns scattered across an enormous rotating disk. Yet even with all of these structures filling the galaxy, the distances between them remain immense. A traveller could move for years or decades without encountering anything but the distant light of stars. Leaving the solar system behind would not look like the scenes often shown in movies. In many films, spacecraft leap away from planets and immediately rush through dense fields of stars, colourful nebulae, and glowing cosmic clouds. The reality would feel very different. The first thing a traveller would notice is how slowly the surroundings change. Even when moving extremely fast by human standards, space remains vast and quiet. Stars that look close together from Earth are actually separated by enormous distances. As a result, the sky would not rush past like scenery outside a car window. Instead, the view would shift gradually, almost imperceptibly at first. Suppose a spacecraft departed from Earth and accelerated far beyond the speeds of any probe humans have launched so far. Once it passed the orbit of the outer planets and crossed the distant regions of the solar system, the sun would begin to shrink behind it. At first, the sun would still appear bright, brighter than any other star in the sky. But with each passing year, it would fade slightly as the spacecraft moved farther away. Eventually, the sun would become just another star among many. That moment might feel surprisingly emotional. The star that once filled the sky with daylight would now appear as a distant point of light, indistinguishable from countless others. From that point forward, the traveller would truly be moving through interstellar space. What does interstellar space actually look like? In simple terms, it looks mostly empty. The distances between stars are so large that even if a spacecraft were travelling at incredible speeds, it might spend years or decades without approaching another star closely enough to notice dramatic changes in brightness. The surrounding sky would still be filled with stars, but their positions would shift slowly over time as the spacecraft moved through the galaxy. One noticeable difference would be the disappearance of familiar constellations. Constellations only appear the way they do because of our particular viewpoint from Earth. The stars that form those patterns are scattered across many different distances. Some are relatively close to us, while others lie hundreds or thousands of light years away. As a spacecraft travelled away from Earth, that perspective would begin to change. Stars that once formed recognizable shapes would gradually drift apart. New alignments would appear as the traveller moved through different regions of space. After a few light years of travel, the constellations seen from Earth would no longer exist in their familiar forms. The night sky would slowly transform. Another difference would be the brightness of nearby stars. When a spacecraft approached a star system, that star would grow brighter over time, much like the Sun appears brighter as Earth moves closer to it during certain points in our orbit. But the change would occur slowly. Even travelling at extremely high speeds, it might take years for a distant star to noticeably increase in brightness. Eventually, the spacecraft might pass through regions of space where stars are slightly more numerous. Open star clusters are one example. These clusters contain groups of stars that form together from the same cloud of gas. Because they were born at roughly the same time and in the same place, they remain loosely bound by gravity as they move through the galaxy. Passing near an open cluster could provide one of the most striking views during a journey across the Milky Way. Instead of a single nearby sun, dozens or hundreds of stars might appear scattered across the sky at relatively close distances. Their light could create a sky far brighter than the night sky seen from Earth. Yet even in these clusters, the stars remain separated by vast distances. Collisions between stars are extremely rare. Another possible sight along the journey would be a nebula. Nebulae are large clouds of gas and dust drifting through the galaxy. Some are the remains of exploded stars, while others are regions where new stars are forming. When illuminated by nearby stars, these clouds can glow with soft colours, producing some of the most beautiful objects in astronomy. The Orion Nebula is one famous example visible from Earth. A traveller moving through such a region might see enormous glowing structures stretching across dozens of light years. Gas clouds could form delicate shapes, lit by the radiation of young stars forming within them. But even nebulae are incredibly large and diffuse. A spacecraft travelling through one would not experience it as a thick fog. Instead, the gas would be so thin that the traveller might barely notice it at all, except for the faint glow of distant illuminated regions. Over time, the spacecraft might approach the spiral arms of the galaxy. Spiral arms are regions where stars and gas are slightly more concentrated. They are also the locations where star formation is most active. Entering one of these arms could bring a gradual increase in the number of visible stars. The sky might appear more crowded, with bright young stars illuminating nearby gas clouds. Stellar nurseries could appear along the path, revealing areas where gravity is slowly pulling gas together to form new suns. But even here, the distances remain immense. The spiral arms of the Milky Way are thousands of light years wide. Crossing one would take centuries or millennia depending on the spacecraft's speed. Eventually, the traveller might approach the central regions of the galaxy. The galactic centre is one of the most crowded environments in the Milky Way. Stars there are packed much more closely together than in our quiet neighbourhood. From a planet orbiting a star near the galactic centre, the night sky might appear dazzling. Instead of a few thousand visible stars, there could be hundreds of thousands scattered across the sky. Some might shine brightly enough to cast faint shadows. However, this region is also filled with thick clouds of dust that block visible light. Much of the galactic centre is hidden behind these clouds when viewed from Earth. Astronomers use infrared telescopes to see through the dust and study the stars within. For a traveller crossing the galaxy, the approach to the central bulge might reveal a sky filled with dense star fields and glowing gas clouds. Deep within that crowded region lies Sagittarius A star, the supermassive black hole at the centre of the Milky Way. Despite its enormous mass, the black hole itself would not appear as a giant swirling vortex unless the traveller approached extremely close. From a safe distance, it would reveal itself mainly through the motion of nearby stars orbiting rapidly around an invisible point. After passing the central bulge, the spacecraft would continue outward toward the opposite side of the galaxy. The environment would gradually become less crowded again as the traveller moved toward the outer regions. Stars would grow more sparse. Nebulae would appear less frequently. the sky would slowly return to the quieter appearance familiar from our own region of the Milky Way. Throughout this entire journey, one thing would remain constant. The galaxy would continue rotating. Stars would drift along their orbits around the galactic centre. Nebulae would evolve as new stars formed within them. Stellar explosions might occur in distant regions, briefly lighting the surrounding space with intense radiation. The galaxy is not frozen in time. It is a dynamic system that changes gradually over millions of years, which means that anyone crossing the Milky Way would witness a slow transformation of the cosmic landscape. New stars appearing, old stars fading, entire regions of gas collapsing into fresh stellar systems, all unfolding across the vast distances of the galactic disk. Time usually feels simple in everyday life. A minute passes, then another. Hours move forward steadily. Days follow nights in a familiar rhythm. Our experience of time seems steady and dependable, almost like a quiet background clock ticking away without interruption. Yet the deeper scientists looked into the universe, the more they discovered that time is not as rigid as it first appears. The passage of time can change depending on motion and gravity. This idea might sound strange at first, but it is one of the most important discoveries in modern physics. For anyone imagining a journey between the stars, understanding this strange behaviour of time becomes essential, because the faster a spacecraft travels, the more unusual time begins to behave. This idea comes from Einstein's theory of relativity. Earlier we discussed how the speed of light acts as a universal speed limit. Nothing with mass can reach that speed because the energy required would become infinite. But something else happens as objects approach that limit. Time itself begins to stretch. Physicists call this effect time dilation. From the perspective of someone watching a fast-moving spacecraft from Earth, the clock on that spacecraft would appear to run slower than a clock on Earth. But from the perspective of the travellers inside the spacecraft, their own clocks would feel completely normal. Their heartbeats, conversations, and daily routines would proceed at the same pace they always have. The difference only appears when comparing the passage of time between the moving spacecraft and the rest of the universe. The relationship describing this effect can be written mathematically, but its meaning becomes clearer when we imagine an example. Suppose a spacecraft could travel at 90% of the speed of light. From Earth's perspective, that speed would still be slightly slower than light itself, but it would be incredibly fast compared with any technology humans currently possess. At that velocity, time aboard the spacecraft would pass more slowly than time on Earth. For every 10 years experienced by observers on Earth, only about 4 years would pass for the travellers aboard the ship. The faster the spacecraft moves, the stronger the effect becomes. If a spacecraft reached 99% of the speed of light, the difference would grow even more dramatic. A journey that lasts 100 years according to observers on Earth might feel like only about 14 years to the travellers. Push the speed even closer to the speed of a light and the effect becomes extreme. At 99.999% of light speed, thousands of years could pass on Earth while only a few years pass aboard the spacecraft. This strange relationship between speed and time creates an interesting possibility for interstellar travel. From the perspective of the travellers, long journeys across the galaxy might feel much shorter than they appear from the outside. Imagine a spacecraft capable of travelling at extremely high speeds, perhaps 99.9% of the speed of light. From Earth's perspective, crossing the Milky Way would still require roughly 100,000 years. But for the crew inside the spacecraft, the journey might feel far shorter. Due to time dilation, the travellers could experience only a few thousand years, or even less depending on their exact speed. This effect does not break the cosmic speed limit. The spacecraft would still be moving slower than light, but the way time flows for the travellers changes the subjective experience of the journey. However, this introduces a new challenge. The travellers might arrive at their destination only a few years older than when they left, but the universe they return to could be vastly different. If someone left Earth on a journey lasting 10 years from their own perspective, while travelling close to the speed of light, they might return to find that hundreds or thousands of years had passed on Earth. Civilizations could rise and fall during that time, languages might change, cities could appear or vanish. The travellers would effectively be stepping forward into the future. This scenario is sometimes called the twin paradox. Imagine identical twins. One remains on Earth while the other travels on a high-speed spacecraft. When the travelling twin returns, they are younger than the one who stayed behind. The reason lies in the way motion through space-time affects the passage of time. Experiments have confirmed that time dilation is real. Atomic clocks carried aboard fast aircraft tick slightly more slowly than identical clocks on the ground. Satellites orbiting Earth experience time differently due to both their speed and the weaker gravitational field at their altitude. Engineers must account for these effects when designing global navigation systems like GPS. Without corrections for relativity, the timing errors would grow quickly, making the system inaccurate. So time dilation is not just a theoretical curiosity. It is a measurable phenomenon that becomes increasingly important as speeds approach the speed of light. But even with this effect, crossing the Milky Way remains an enormous challenge. The energy required to accelerate a spacecraft to relativistic speeds would be staggering. The faster the spacecraft moves, the more energy is needed for each additional increase in speed, and there are practical concerns beyond energy. A spacecraft travelling at such extreme velocities would encounter tiny particles of dust and gas drifting through interstellar space. At near-light speeds, even microscopic particles could carry enough energy to damage the spacecraft upon impact. Shielding the vessel from such collisions would be an enormous engineering challenge. Radiation would also become more intense. Cosmic rays and high-energy particles could pose serious risks to any crew aboard the spacecraft. Protecting travellers from these hazards during a journey lasting decades or centuries would require advanced technologies that humans are only beginning to imagine. Another issue is communication. Signals travelling between the spacecraft and Earth cannot exceed the speed of light. As the spacecraft moves farther away, messages would take longer and longer to arrive. At distances of thousands of light years, communication delays would stretch across centuries. The travellers would effectively be on their own. Despite these challenges, the concept of relativistic travel remains fascinating. It reveals that time and motion are deeply connected in ways that are not immediately obvious in our everyday experience. The faster we move through space, the slower we move through time relative to others. This relationship shapes the possibilities and limitations of any journey across the galaxy. Even with time dilation shortening the perceived travel time for the crew, the Milky Way remains vast enough that crossing it would still require incredible technological advances and enormous amounts of energy. But humans are creative problem solvers. Throughout history, we have found ways to explore environments that once seemed unreachable. Oceans that once felt impossibly wide eventually became routes of exploration. The skies that once seemed inaccessible are now crossed by airplanes every day, and today spacecraft routinely visit other planets in our solar system. Travel across the galaxy does not necessarily require travelling extremely fast. Another possibility involves accepting the enormous distances and simply allowing the journey to take a very long time. Instead of racing across the stars in a single lifetime, a spacecraft could become a moving world of its own. The people who begin the voyage would know they will never see the destination. Their children might not see it either. The travellers who eventually arrive could be the distant descendants of the original crew. Ideas like this are often called generation ships. A generation ship is exactly what the name suggests. It is a spacecraft designed to carry multiple generations of people across interstellar distances. The ship itself would function almost like a small artificial planet. Inside it, communities would grow, work and raise families, while the vessel slowly travels toward another star. From a practical point of view, this approach avoids the need for extreme speeds. If a spacecraft travelled even a tiny fraction of the speed of light, it could still reach nearby stars eventually. For example, Imagine a vessel moving at 1% of the speed of light. That speed might sound slow compared with the theoretical limits discussed earlier, but it's still extremely fast by human standards. 1% of light speed is about 3,000 kilometers per second. At that pace, the spacecraft would cross 1 light-year of distance in roughly 100 years. Reaching Alpha Centauri, the nearest star system, would take about 400 years. For a normal human crew, 4 centuries is far longer than a single lifetime, but for a generation ship, that span of time might be manageable. The people who launched the vessel would live their lives aboard the ship. Their children would grow up there. Those children would eventually become the adults responsible for guiding the ship's systems and continuing the journey. Over time, a new society would develop inside the spacecraft. The ship would need to be completely self-sustaining. It could not rely on supplies from Earth because the journey would last far too long. Food, water, and air would all need to be recycled continuously. Plants might grow in carefully managed agricultural systems, producing oxygen and food at the same time. Waste materials would be processed and reused. Every resource would need to circulate within the closed environment of the ship. Designing such a system would be an enormous engineering challenge. Even the International Space Station, which supports astronauts in orbit around Earth, depends heavily on regular resupply missions. A generation ship travelling through interstellar space would not have that luxury. Everything needed for survival would have to function reliably for centuries. Engineers sometimes imagine these ships as large rotating structures. The rotation would create artificial gravity through centrifugal force. As the ship spins, people standing inside the outer ring would feel a force pushing them toward the floor, similar to the sensation of gravity on Earth. Without some form of artificial gravity, long-term life in weightlessness could cause serious health problems. Bones lose density, muscles weaken, circulation changes. Creating a rotating habitat could help maintain normal living conditions during a long journey. Inside such a vessel, life might resemble life in a small, isolated town. There would be living areas, farms, water recycling systems, energy generators, and control rooms monitoring the ship's trajectory. Children born aboard the ship would grow up knowing that their world is a spacecraft moving between the stars. They might learn about Earth through history lessons or preserved recordings. For them, Earth would be more like a distant ancestral home than a familiar place. Generations would pass as the ship slowly approached its destination. One of the most difficult questions surrounding generation ships is social stability. Maintaining a functioning society over centuries requires careful planning. Conflicts, disagreements, and cultural changes could affect the mission. The travellers would need systems of governance, education, and cooperation capable of lasting far longer than any existing human institutions. Some researchers have explored these questions using computer simulations and studies of isolated communities on Earth. The goal is to understand how a closed society might remain stable over long periods. Another challenge involves the size of the initial population. If the crew is too small, genetic diversity could become a problem over many generations. Scientists studying this issue suggest that a population of several thousand people might be necessary to maintain a healthy gene pool across centuries. Providing enough space, food, and resources for such a population would require a very large spacecraft. Some proposed designs imagine generation ships kilometers in length. Inside them could be forests, lakes, farmland, and residential areas designed to support long-term human life. Energy for the journey might come from nuclear reactors or other advanced power systems capable of operating for centuries. Because the ship would travel slowly compared with the speed of light, its engines might run only occasionally to make small adjustments to its trajectory. Most of the time, the ship would simply coast through space. From the perspective of the people living aboard, the outside universe would appear almost motionless. Stars would shift their positions very gradually over the course of decades. The galaxy would change slowly, almost imperceptibly. For those travellers, the spacecraft would be home in the deepest sense of the word. Their entire lives would unfold within its walls. They would celebrate birthdays, hold gatherings, learn new skills, and watch children grow up under artificial sunlight. Generations would come and go as the vessel quietly crossed the immense distances between stars. Eventually, many centuries after the journey began, the ship would approach its destination. The descendants of the original crew might finally see another star growing brighter in the sky ahead. Perhaps that star would host planets suitable for settlement. Perhaps the travellers would establish a new human presence there, beginning another chapter of exploration. Yet even generation ships face limits when we think about crossing the entire Milky Way. At 1% of the speed of a light, crossing the galaxy would still take roughly 10 million years. That is far longer than the lifespan of any civilization humans have known. Even if thousands of generations lived and died aboard such a ship, the journey across the full width of the galaxy would remain incomplete for an incredibly long time. Because of this, many scientists believe that realistic interstellar travel will focus on reaching nearby stars rather than crossing the entire galaxy. Still, imagining generation ships helps reveal how vast the Milky Way truly is. It reminds us that the distances between stars are not just large, they're so immense that journeys across them might require entirely new ways of thinking about travel, time, and human society. Distances in the galaxy feel overwhelming when we imagine travelling through them in the ordinary way. Even with spacecraft far faster than anything humans have built so far, the journey from one side of the Milky Way to the other stretches across millions of years. The stars are simply too far apart and the galaxy itself is too wide. Because of this, physicists and science fiction writers have both wondered whether there might be shortcuts hidden within the structure of space itself. Instead of travelling the entire distance from point A to point B, perhaps there is a way to fold space so that those points become neighbours. One idea that explores this possibility is known as a wormhole. The concept first appeared in serious physics discussions during the early 20th century. It emerged naturally from the equations of general relativity, the theory Albert Einstein developed to describe gravity. In general relativity, gravity is not simply a force pulling objects together. Instead, massive objects bend the geometry of space-time around them. Planets orbit stars because they are following curved paths through this warped space-time. If space-time can bend and curve, then the equations also allow for more unusual shapes. Among those shapes is a structure connecting two distant regions of space-time through a tunnel-like passage. That structure is what physicists call a wormhole. A simple way to picture it is with a sheet of paper. Imagine 2 points drawn on the sheet, far apart from each other. The normal way to travel between them is to move across the surface of the paper in a straight line. But if you fold the paper so the 2 points touch, the distance between them becomes extremely small. A traveller could pass directly from one point to the other through the fold. A wormhole would act like that fold in space-time. Instead of travelling across tens of thousands of light years, a spacecraft might enter one end of the wormhole and emerge almost instantly at the other end. If such structures existed and could be used safely, they would completely change the challenge of crossing the galaxy. The entire Milky Way could become navigable in a matter of minutes or hours rather than tens of thousands of years. However, the idea raises many difficult questions. First, do wormholes actually exist in nature? The mathematics of general relativity allows them, but that does not guarantee they form naturally in the universe. Some physicists believe that tiny wormholes might appear briefly at extremely small scales due to quantum effects. These microscopic wormholes would exist for only fractions of a second before collapsing. Such fleeting structures would be far too small to allow anything macroscopic to pass through them. Creating a stable wormhole large enough for a spacecraft would require very unusual conditions. One of the biggest obstacles involves something called exotic matter. According to current theoretical models, keeping a wormhole open would require matter with negative energy density. This type of matter would behave very differently from the matter we encounter in everyday life. Ordinary matter always has positive energy. Exotic matter, by contrast, would exert a kind of gravitational repulsion that could hold the wormhole's throat open against collapse. Small effects resembling negative energy have been observed in certain quantum experiments, such as the Casimir effect, where two closely spaced metal plates experience a tiny attractive force caused by changes in the quantum vacuum between them. However, the amounts of negative energy involved in these experiments are extremely small. Creating enough exotic matter to stabilize a wormhole large enough for human travel would require physics far beyond anything we currently understand. Another challenge is stability. Even if a wormhole could be created, keeping it stable might be extremely difficult. The intense gravitational forces surrounding such a structure could cause it to collapse rapidly or generate dangerous radiation. Travelling through a wormhole might expose a spacecraft to extreme conditions that current technology could not withstand. There is also the question of navigation. A wormhole would connect two locations in space-time, but controlling where those locations are could be complicated. If one end of the wormhole moved or shifted unpredictably, the exit point might not lead where the traveller expects. Despite these challenges, wormholes remain a fascinating idea in theoretical physics. They appear not only in the mathematics of general relativity but also in some modern theories attempting to unify gravity with quantum mechanics. Researchers continue to explore whether stable wormholes could exist in principle, even if building one remains far beyond current capabilities. Interestingly, wormholes also raise questions about time. Because space-time itself is involved, certain configurations of wormholes might allow paths that loop backward through time. This possibility has led to many debates among physicists about whether the laws of nature prevent such paradoxes from occurring. Some researchers believe that unknown physical principles may forbid time-travelling wormholes altogether. Others argue that the mathematics does not clearly rule them out. For now, wormholes remain in the realm of theoretical exploration. They represent one possible way that the enormous distances between stars and galaxies might be bridged. But until evidence for such structures appears, interstellar travel must still rely on the ordinary geometry of space, which means the vast distances of the Milky Way remain very real. Even the nearest stars require years to reach at the speed of light. Crossing the entire galaxy would take 100,000 years at that ultimate speed. The universe seems to have arranged its scales in a way that makes rapid travel extremely difficult. Energy is the quiet requirement behind every journey ever made. A person walking across a field uses chemical energy stored in their muscles. A car crossing a continent burns fuel inside its engine. A rocket climbing away from Earth consumes enormous quantities of propellant simply to escape the planet's gravity. Movement always has a cost. The faster something travels and the farther it must go, the more energy is required. For everyday transportation, the numbers remain manageable. Even an airplane crossing an ocean uses only a tiny fraction of the energy available on Earth. But when we begin thinking about crossing a galaxy, the scale of the energy required becomes almost unimaginable. To understand why, it helps to begin with the most basic relationship between energy and motion. When an object moves, it carries kinetic energy. The faster it moves, the more kinetic energy it has. For ordinary speeds, the amount of energy required to accelerate something can be estimated using a simple expression from classical physics. E sub k equals 1/2 mv squared. In this equation, E sub k represents kinetic energy, m is the mass of the object, and v is its velocity. The important detail here is the square of the velocity. If you double the speed of an object, the energy required does not merely double, it increases by a factor of 4. If you increase the speed 10 times, the required energy becomes 100 times larger. This relationship is manageable for cars, airplanes, and even rockets. But when speeds approach a significant fraction of the speed of light, the numbers begin to grow extremely quickly. Now imagine a spacecraft designed for interstellar travel. Such a vessel would not be small. Even a minimal crewed spacecraft capable of supporting life for many years might weigh thousands of tons. Larger concepts such as generation ships or rotating habitats could weigh millions of tons. Let us consider a modest example. Suppose a spacecraft with a mass of 1,000 tons, that is about the mass of a large naval ship. needed to accelerate to just 10% of the speed of light. 10% of light speed is about 30,000 kilometers per second. Plugging that velocity into the kinetic energy equation produces an enormous number. The energy required would be roughly equivalent to the energy released by many thousands of nuclear bombs, and that is only to accelerate the spacecraft. A real mission would require even more energy, because the spacecraft must also slow down when it reaches its destination. Accelerating to high speed is only half of the journey. Decelerating requires the same amount of energy again, unless some clever gravitational assist could be used. This doubling of the energy requirement means that even a relatively slow interstellar journey demands extraordinary power. And remember, 10% of the speed of light is still far too slow to cross the Milky Way in any reasonable time frame. At that speed, crossing the galaxy would take about 1 million years. Increasing the spacecraft's speed to shorten the journey makes the energy problem even worse. As speeds approach the speed of light, classical physics no longer gives accurate results. Relativity takes over, and the energy required rises even more steeply. The relationship between energy and mass becomes central in this regime, E = mc². This equation shows that mass itself contains an enormous amount of energy. Even a small amount of matter can produce tremendous energy if converted efficiently. The equation also hints at why accelerating massive objects to near-light speeds becomes so difficult. The energy required grows toward infinity as velocity approaches the speed of light. In practical terms, this means that no realistic engine can push a massive spacecraft all the way to light speed. Even reaching a fraction of that speed would require staggering amounts of energy. To get a sense of the scale, consider the total energy consumption of human civilization today. All the power plants on Earth combined produce roughly 20 trillion watts of power. That sounds like a large number, and it is. But accelerating a 1,000-ton spacecraft to relativistic speeds would require energy far beyond the total energy production of humanity for many years. This challenge leads scientists and engineers to explore different ways of generating or storing the necessary energy. One possibility involves nuclear fusion. Fusion is the process that powers stars, including our Sun. In a fusion reaction, light atomic nuclei combine to form heavier nuclei, releasing energy in the process. Fusion produces far more energy per unit of fuel than chemical reactions like burning gasoline or rocket fuel. Some proposed spacecraft designs use fusion reactors to generate thrust. By fusing hydrogen isotopes and directing the resulting plasma out the back of the spacecraft, a fusion engine could produce continuous acceleration for long periods. Even so, fusion propulsion would still struggle to reach speeds much higher than a few % of the speed of light. Another idea involves antimatter. Antimatter is the mirror counterpart of ordinary matter. When matter and antimatter meet, they annihilate each other completely, converting their entire mass into energy. This process is incredibly efficient. A small amount of antimatter could release enormous energy. In theory, antimatter propulsion could accelerate spacecraft to significant fractions of the speed of light. However, antimatter is extremely difficult to produce and store. Modern particle accelerators can create tiny amounts of antimatter, but the quantities are measured in nanograms. Producing enough antimatter to power an interstellar spacecraft would require technology far beyond anything currently available. Even storing antimatter safely presents enormous challenges, since it must be kept from touching ordinary matter. Another concept sometimes discussed is the idea of light sails. A light sail is a large reflective sheet attached to a spacecraft. Powerful lasers or sunlight push against the sail, gradually accelerating the spacecraft without the need to carry large amounts of fuel. Projects such as Breakthrough Starshot are exploring this idea using extremely small spacecraft. In these proposals, powerful lasers on Earth would accelerate tiny probes to speeds approaching 20% of the speed of light. Even at those speeds, however, crossing the Milky Way would still require hundreds of thousands of years. These energy challenges reveal something fundamental about the universe. Distance is not the only obstacle to travelling across a galaxy. Energy is just as important. The Milky Way is not only large in terms of kilometres or light years, it is large in terms of the energy required to move through it. Every increase in speed demands exponentially more energy. Every additional kilogram of spacecraft mass multiplies the problem further. The galaxy quietly resists rapid travel simply through the laws of physics. Yet this does not mean that exploring the galaxy is impossible. It only means that such exploration must respect the limits imposed by energy and time. Future civilizations might develop technologies that generate far more energy than humanity currently produces. They might learn to harness the power of entire stars or create propulsion systems far more efficient than those we know today. Even then, the vast scale of the Milky Way would remain. The galaxy stretches across 100,000 light years. No engine, no matter how powerful, can erase that distance entirely. Which leads to an interesting realization. Perhaps crossing the galaxy is not the most important goal. The Milky Way already contains hundreds of billions of stars, each potentially hosting its own planets and environments. Exploring even a small fraction of those systems could take countless generations. In other words, the galaxy may be so rich with possibilities that travelling across its entire width is not necessary to discover its wonders. Movement across the galaxy is not something that only spacecraft might experience someday in the distant future. In a quiet and almost unnoticed way, the journey has already begun. Every person listening to this right now is already travelling through the Milky Way. The motion is not dramatic. There are no rushing winds of space or flashes of passing stars. Your room feels still. The ground beneath you feels steady. Nothing in your everyday surroundings suggests that you're moving at extraordinary speed. Yet the entire solar system is drifting through the galaxy at a remarkable pace. The Sun, along with all of its planets, asteroids and comets, orbits the centre of the Milky Way once every few 100 million years. That orbit carries us through the galaxy at roughly 800,000 kilometers per hour. To make that number easier to picture, imagine a spacecraft moving at that speed around Earth. It would circle the planet several times every hour. But the Sun is not racing across the galaxy in a straight line. Instead, it follows a curved path around the galactic centre, guided by the gravity of the billions of stars surrounding it. That path is so large that completing a single orbit takes about 230 million years. Astronomers sometimes call this span of time a galactic year. A galactic year is very different from the familiar year we experience on Earth. Our planet completes one orbit around the Sun every 365 days. The solar system completes one orbit around the Milky Way only once every 230 million Earth years. That means the last time our planet was in roughly the same position in the galaxy, dinosaurs were just beginning to appear on Earth. Forests looked different. The continents were arranged differently. Mammals were small creatures living in the shadows of much larger reptiles. Since then, Earth has travelled an enormous distance through space as part of the Sun's orbit. In fact, during the time it has taken you to listen to this story, the solar system has already moved thousands of kilometers through the galaxy. None of us feel this motion because everything around us is moving together. The planet, the oceans, the atmosphere, and even the spacecraft orbiting Earth all share the same journey. From our perspective inside this moving system, everything appears calm and stationary. But if you could step far outside the galaxy and watch the Milky Way from a distance, the motion would become clear. The galaxy would appear as a great spiral disk slowly turning in the darkness. Its arms would sweep through space as stars traced graceful orbits around the centre, and somewhere within that rotating disk, one small yellow star would carry a collection of planets along with it. One of those planets would be Earth. The journey of the solar system is not perfectly smooth. As the Sun orbits the galactic centre, it also moves slightly above and below the galactic disk in a gentle wave-like motion. This oscillation takes tens of millions of years to complete. At the moment, our solar system happens to be passing through the middle region of the disk, surrounded by nearby stars drifting along their own orbits. Over time, the Sun will slowly rise above the galactic plane before drifting back downward again. These motions are subtle and slow, but they are part of the complex gravitational dance that shapes the Milky Way. Even the direction of the solar system's orbit is not perfectly aligned with the galaxy's spiral arms. The spiral arms are not rigid structures. They behave more like waves moving through the galactic disk. Stars drift in and out of them over time. Billions of years ago, the Sun likely formed within one of these spiral arms from a cloud of gas and dust. Since then, it has travelled across different regions of the galaxy during its long orbit. Each region of the Milky Way has its own characteristics. Some areas are dense with star-forming clouds and young bright stars. Other regions contain older stars that have been shining for billions of years. Our solar system currently resides in a relatively quiet area known as the Orion Arm, a smaller branch located between two larger spiral arms. This location may have been fortunate for life on Earth. Regions closer to the galactic centre experience more frequent supernova explosions and higher levels of radiation. Those environments could make the development of stable planetary systems more difficult. Farther out in the galaxy, heavy elements such as carbon, oxygen and iron become less common. These elements are essential for building rocky planets like Earth and for supporting complex chemistry. The Sun's position about halfway between the centre and the outer edge of the Milky Way appears to be a comfortable place for a planetary system to exist for billions of years. As the solar system continues its orbit, the sky visible from Earth will slowly change. Stars drift through the galaxy, and the patterns of constellations gradually evolve. If someone living today could watch the night sky for hundreds of thousands of years, they would see the familiar shapes of Orion, Ursa Major, and other constellations slowly distort. Stars that appear close together from our viewpoint would drift apart as their individual motions carried them through the galaxy. New patterns would form in their place. Over millions of years, the night sky would look completely different. The galaxy itself will also continue evolving. Stars will be born from collapsing clouds of gas. Others will reach the ends of their lives and explode as supernovae. Those explosions will scatter heavy elements across the galaxy, enriching the gas clouds that eventually form new generations of stars and planets. This cycle of stellar birth and death will continue for billions of years. During that time, the Milky Way will also experience encounters with other galaxies. One of the most dramatic of these events is expected to occur about 4 billion years from now, when the Milky Way and the Andromeda Galaxy begin to merge. At present, Andromeda lies about 2.5 million light-years away from us. But the two galaxies are slowly moving toward each other under the influence of gravity. When they finally meet, their stars will pass through one another in a vast gravitational interaction lasting billions of years. Despite the enormous number of stars involved, direct collisions between individual stars will remain extremely rare because the distances between them are so large. However, the overall shape of the galaxy will change dramatically. The graceful spiral arms of the Milky Way may dissolve into a new, larger galaxy with a different structure. By that time, the Sun will be approaching the end of its life. Several billion years from now, the Sun will expand into a red giant star, likely engulfing the inner planets of the solar system. Long before that distant future arrives, humanity may have spread beyond Earth, perhaps even beyond the solar system. But whether humans eventually explore nearby stars or remain close to home, the solar system itself will continue its quiet journey through the galaxy. We are passengers on a moving world. The Earth spins beneath our feet. The planet orbits the Sun. The Sun orbits the centre of the Milky Way. And the Milky Way itself is drifting through the universe along with billions of other galaxies. This layered motion means that every moment we're travelling through space in ways that are easy to overlook. Crossing the entire galaxy intentionally may remain far beyond our technological abilities for a very long time. Yet in another sense, we're already part of a journey across the Milky Way. Our solar system has been travelling through the galaxy for billions of years. It will continue that journey for billions more. And somewhere in the distant future, Long after the stars visible tonight have shifted into new patterns, the descendants of our civilization may still be riding along with this quiet galactic voyage.